was a groundbreaking space probe that was designed to mainly study the planet Mercury, an accomplishment that wouldn't happen again for more than 30 years. It was also the first spacecraft to explore 2 planets during a single mission, the first to use a gravity assist to change its flight path, and the first to return to its target after the initial encounter. Despite several mechanical problems during the mission, which included malfunctions in the high-gain antenna and the attitude control system, NASA persevered with the struggling spacecraft, which ultimately provided them with a lot of scientific data. After a couple of mid-course corrections, Mariner 10 was set on a flight path that would initially take it to Venus, where it would complete the first ever gravity assist maneuver, a practice that is now a standard part of space navigation. After receiving the gravity boost, Mariner 10 then had the right speed and trajectory to take it all the way to Mercury, placing it into an orbit around the Sun that would allow multiple flybys of the solar system's innermost planet. But before Mariner 10 would ever make it to Mercury, it would first have to test and calibrate its 2 onboard cameras. These grainy but incredible images were taken shortly after the launch, as the spacecraft was leaving the Earth's atmosphere. Several hundred photographs were snapped, giving the imaging team the chance to make sure that the cameras were working correctly in preparation for the main mission. Many of the photos east towards its first destination, and in February 1974, just 3 months after its launch, the spacecraft arrived at Venus. This mosaic is made up of 78 photographs that were captured through orange and UV filters. By using these filters, we can see Venus in a natural colour while revealing some of the planet's mysterious cloud features. Because Venus is shrouded in a thick, dense atmosphere, the planet is normally observed as a hazy, pale yellow ball, showing a world that is generally featureless in visible light. But by using an ultraviolet filter, Mariner 10 was able to capture Venus in a way that had never been seen before. This incredible image has been colour enhanced to bring out the cloudy atmosphere of Venus as the human eye would see it. It exposes an active atmosphere that is swirling around the planet's scorching surface. During its flyby, Mariner 10 snapped thousands of photographs of Venus, and by processing many of the images into mosaics, it was possible to make a time-lapse of the planet that reveals the rotation of the Venusian atmosphere. The grainy video lost in our star's solar glare, but in March 1974, about 7 weeks after its Venus flyby, Mariner 10 had finally arrived at Mercury. This mosaic revealed Mercury just 6 hours before Mariner 10's closest approach, showing us a planet that is very much like our moon, a barren landscape that is covered in basins, craters, ridges, and plains. After passing the dark side of Mercury, Mariner 10 gave us an outbound view of the planet, exposing a somewhat illuminated hemisphere. Because of Mariner 10's trajectory, the spacecraft looped around the Sun while Mercury completed its own orbit, allowing Mariner 10 the chance to encounter the strange worlds a second and a third time. The second flyby occurred in September 1974, and the third in March 1975. These close-up images give us an incredible view of the planet's strange landscape that is scarred with large-scale lava flows and riddled with craters that occurred during the ancient bombardment. Shallow radial ridges can be seen at the edges of the impact craters.
Do I know Anton Petrov from McGill University? Anton. I think I was just watching his video, to be honest, man.
A huge crater that is approximately 960 miles in diameter and is surrounded by
What's going
concentric rings
on,
of towering
VFX? How you
mountains.
doing, homie? Yeah, I was literally just watching. He's from McGill? I didn't know that. I didn't know that, man.
Hello and focus on this is Anton, and today we're going to be talking about the sister planet of Earth, Venus, and more specifically about a
That's cool.
very exciting mission that NASA is planning for the next few years, and the contest that was just run by NASA.
That's sick, dude. I didn't know it's from McGill University. That's awesome, man.
And winners. But we'll also talk a little bit more about the planet itself and why it's an
So,
exciting
yeah,
opportunity
he
for
just,
us to
we
advance
just, well, I
and
just watched a
potentially
video on
find an incredible
the
object for us to
discovery of
colonize. Let's talk
phosphine
about this and welcome to it.
on Venus, which is apparently this gas that is 10,000 times higher than any chemical reaction would make, apparently. Apparently on Earth we only know that
But I wanted
phosphine
to
is made
start
by
with a little
bacteria.
bit of history. This right here is.
So he's
what's
arguing
known
that we should
as
go to
the Vega
Venus?
probe.
That's
This
what
was
he
a
did in the last
Soviet
video.
probe launched in the 80s.
That's sick,
It was
man.
the last
Apparently you
attempt
watched
by the
that?
Soviets to land on Venus and
Nice.
essentially try to retrieve as much data as possible. When it comes to planetary exploration, the Soviet Union and Russia didn't really have a lot of luck with Mars. Most of the missions here were from NASA, but they had tremendous success with the partner Venus. And most of the information and most of the data we have about Venus is from the Soviet Union, from the Soviet space program. So for example, the first ever picture of the surface of Venus, along with the information on the temperature, the pressure, the composition, were all more or less accomplished by the Soviet Venera and other similar missions that were able to survive for a few hours on the surface of Venus.
Good to hear from you,
and
man.
early on, we realized how extremely inhospitable Venus was, not just to life, but even to the instruments sent to the planet. Essentially, nothing here survived for longer than a couple of hours, unless it was in the upper atmosphere. One of the last missions that Soviets were able to succeed in were actually part of the Vega mission you see right here, and were these extremely robust balloons with a lot of instruments and communication devices attached to them that would fly around the upper atmosphere, collecting all of the data and transmitting it via the orbiter around Venus. Now obviously this would have continued for a long time if USSR survived. We might have had even some sort of an aerial colony by now if we continue these missions, but USSR is gone, Russia is no longer continuing Venus missions, and other agencies including NASA have only now started to pick up where it was basically left a few decades ago.
Yeah,
But
I don't know
honestly,
Anton
the new
personally. I know
NASA
he's a
missions
Russian that
are
went to school in
absolutely
McGill. Oh, no way.
brilliant. And they're brilliant
That's
for
sick,
a
man.
very unusual reason. And
He's a
what's
smart guy.
important here is that it might lead to a creation of an incredible new type of technology that
Yeah,
we've never had
I've actually,
before. But more accurately,
yeah, I found
it
his
might
videos
actually
maybe
lead
like
to the
a week or two ago.
re-explosion of the so-called automata, or mechanical technology. Something that was created in the ancient world and mostly for entertainment purposes, and something that was actually created over 2,000 years ago, such as,
This is too theoretical. I mean,
for example, this right here. This
well, it's not
is the
theoretical. It's very
famous
historical.
Antikythera mechanism that was created most likely over 2,000 years ago by the Greeks to try to predict the motion of the planets across the sky. But there were these unusual automata in very different cultures across the planet, and many of them were extremely advanced, but pretty much all of them were more or less only used for entertainment or recreation.
yo, sick. If you have a favorite one of his, we could put it on. He has a bunch of videos. How you doing, man? Hope you're good, dude.
Hello, this is a planet known as Ceres, located in the asteroid belt. And somewhere in the orbit of this dwarf planet, there's a beautiful NASA probe known as Dawn that's been there for a few years now. This probe is known for setting a new record in ion engine propulsion by allowing it to change its velocity by about 11.5 kilometers per second or 26,000 miles a few years ago when it was changing its orbit from Vesta to Ceres. But in the last few years there were also a lot more advances in the ion engine technologies, and I wanted to talk about them in this video. So let's discuss this in more detail, and welcome to the Math. So generally, when we think of rocket engines, this is what we kind of imagine. But many of you know that there are also ion engines that have been in use for a long time now, and they're also quite powerful, but in a different sense. While a typical rocket engine has a lot of power to lift an object and to take it into space, the advantage of an ion engine is that it can actually use a lot less fuel to achieve the same type of velocity that a typical
although I'm not
rocket
sure if he has
engine could
VC
achieve.
and F
But because their
or
overall
whatever.
power is much lower
Yeah, he
than a
seems super
typical
knowledgeable,
rocket
man.
engine, we
He
can't
seems
just
like
use ion engines to
well, he
lift
seems
objects.
like
For
he's
now,
up to
the
date
ion
with the
engines
science
have
because
really only been used
he
in
references
space
new science
and in
in his
conditions
works,
where there's
you know?
no air friction and no gravity to worry about. And although a typical
So it
ion
looks like he's
engine
up to
cannot
date.
really lift anything from planet Earth, they're still extremely efficient. Normally, this type of an engine using liquid hydrogen and liquid oxygen would produce roughly around 10 megajoules per kilogram of fuel, whereas the ion engine inside the Dawn probe was able to produce approximately 43 times more energy out of the same amount of fuel. But the fuel here is of course different.
Thinking about the future of space, there's usually one planet that comes to mind: Mars. Whether it be rovers that have explored the red planets, Elon Musk's vision for a future colony, or even the name of this YouTube channel, we usually get pretty excited about Mars. But what if I told you we might be mistaken?
So Anton
Let's
says we
talk
should
about
go
that.
to Venus first. He said forget about Mars. He said go to Venus. It's like, what?
As you probably noticed from the title of this video, we are going to be talking about the planet Venus, the second closest planet to the Sun, known for its massive atmosphere and high surface temperatures. But why would we want to explore Venus? It turns out that Venus can tell us a lot about the evolution of terrestrial planets, because it's theorized that Venus could have potentially been habitable in the past. It could have been an oasis in our solar system, but now it's the hottest planet and essentially uninhabitable right now. So how did it go from an oasis to what it is today? Understanding this can give us a lot of insight into what we should be looking for in exoplanets around other stars. So how do we go about exploring Venus? The best way to do this is to compare it to exploring Mars. What are the differences between the two? So first, let's talk about just sending a robotic mission to these two planets. It turns out that if we wanted to send a mission to Venus, it would take roughly 3 months to get there, whereas if we sent a mission to Mars, it takes anywhere from 8 to 9 months.
Wow.
In addition, it takes
Venus.
roughly the same amount of fuel to go to Venus or Mars, but sometimes it's more efficient to go to Mars and sometimes it's more efficient to go to Venus, just depending on what you want to do once you get there. In addition, if you want to use solar panels, it's actually 4 times more effective to go to Venus than it is to go to Mars.
Wow.
However, that efficiency of 4 times starts to decrease
Yeah, it seems
as you
like
start to enter the atmosphere of
he
Venus.
provides good information,
So
though.
far it sounds like it's actually easier to go to Venus than it is to Mars.
I
However,
read-
some of
I
the
read your
challenges
comment. I
start
just wanna
to
talk
arise
over
when
the
we
guy
enter
right
the
now.
atmosphere at Venus. The surface temperature of Venus is 464 degrees Celsius, and the atmospheric pressure is 91 times the atmosphere here on Earth. Whereas on Mars, the average temperature is negative 63 degrees Celsius, and the average pressure is only 0.6% of Earth's atmosphere. So you might be thinking, well, Mars is really cold and has a really small atmosphere, and Venus is really hot and has a large atmosphere. So we can design missions to go to either of these places, right? Well, it turns out it's easier to deal with the cold than it is the warmth. Let me give you an example. Let's look at our friend the Opportunity rover. It was able to survive through the harsh winters on Mars because it had electronics to keep it warm. You see, these electronics emitted heat, which essentially kept it within its operable temperature range, which meant that essentially Opportunity had its own personal heater that it could use on Mars, and therefore it lasted nearly
for
15
sure.
years on the surface of Mars. Whereas if we go to Venus, the first Venera lander had to survive these high
But it's
temperatures
interesting
and
'cause
high
who else
pressures
would be up to
once
date
it hit the surface.
on,
and it only lasted for
on
50
new scientific
minutes.
papers
So again,
that
when we
have
compare
come
the
out,
cold environment
other
to
than
the
someone
hot
who's
environment,
kind
it's
of
much
into
easier
that,
to
you know what I
survive
mean?
somewhere where it's colder than it is where it's incredibly hot. Just because
could be
it's
out of
hard to get to Venus
research
doesn't make it
and
impossible.
just do this full
In
time.
fact, researchers at NASA Glenn have
it's
been
cool,
able
man.
to
It's
develop
cool, you know, we get to
electronics
see-
that could survive the harsh environment
We
on
get to learn
Venus.
from, like,
So
leading experts, you know
why
what I mean?
aren't we going?
Like, I don't know-
In
I
fact,
don't know
if
much
NASA
about,
really wanted to, they could probably put together a mission and send it by the
I don't
late
have any, like,
2020s.
professional training
However,
in
that's not
astronomy
happening.
and
And you might be thinking right now, well, I still
geology.
prefer Mars over Venus, no matter what you say in this video. And that's
And
perfectly fine.
planetology.
Mars is a truly
Whatever
fascinating
it's called.
planet. But all I want to get across is that Venus needs a little bit more attention. And let me tell you why. The last time NASA sent a spacecraft just to study Venus was in May of 1989, nearly 31 years ago. And you might not know this, but NASA has never landed anything on the surface of Venus. Only the Soviet Union has. Now, to put this into perspective, since May of 1989,
Venus sounds like it
NASA
sucks.
has sent 16 missions to Mars,
Yeah,
not including
Mars
2 CubeSats.
seems like the place
so
to be, man.
16 versus
Why
1
would he go to
over the
Venus?
last 31 years. That's a pretty low ratio. And recall that it's almost as easy to go to Venus as it is to Mars. I'm surprised that NASA hasn't sent more missions to Venus. That just goes to show how much we haven't gone to Venus in our history, and there's so much more that we can learn. I should mention that there are other agencies that have gone to Venus, the most recent one being JAXA. However, there needs to be more exploration if we really want to understand more about the planet, which is pretty straightforward. But what about the future? It turns out it might be easier to send astronauts to Venus than to Mars.
I used
But
to talk to
why?
a guy that helped
The first
design the
reason is because
Cassini
of
probe
Venus's
that they
gravity.
flew down to
Venus
the moon.
is slightly smaller than Earth, but the
To a
gravity is
moon.
roughly 90% of Earth's gravity.
Wow,
whereas Mars's
I'm
gravity
gonna
is
find
only
a video on the
38%
Cassini
of
probe
Earth's
after,
gravity.
dude.
And you might be wondering,
sounds
what do these
amazing.
percentages have to do with sending people
Heck
there?
yeah, man.
And the reason is because some of the largest health hazards of going into space have to do with the lack
How
of
did
gravity.
you know that person?
When
How did you get to
astronauts
meet
are
that person?
weightless in the International Space Station, they experience a lot of issues, some of which being bone mass loss, muscle loss, even issues with their eyesight as well as cardiovascular system, which could be a major issue. And scientists aren't sure if the same things will exist when we get to the moon or Mars. However, if they're on a planet that has the closest gravity to Earth, then more than likely it would make sense for them to be healthier. So it's interesting to note that going to Venus might actually be healthier for astronauts than going to Mars. Another major health hazard of space exploration is astronauts' exposure to radiation. And here again, Venus has a major advantage. The atmosphere around Venus would protect astronauts way better than Mars's atmosphere would. In fact, it wouldn't even be a problem if you went to Venus. So
Interesting.
it's interesting to note some of the comparisons between these two planets. Now you might be thinking Venus is too hot for us to live on. And the answer to that is we don't have to live on the surface. Scientists believe that we could actually fly around in an airship in the upper atmosphere of Venus. At an altitude of 50 kilometers above the
Fucking
surface of
airship? Are you
Venus,
kidding me?
it would actually be just right for human exploration.
No
The
fucking way
atmospheric
I'm
pressure
living
would
in an
be
airship.
equal to the atmospheric
Be like
pressure here on Earth,
Zeppelin,
meaning it would feel
like Led
normal.
Zeppelin.
It would be a little hot at 75
Hindenburg.
degrees Celsius, but you could wear a heat suit to deal with this. And if you had a supply of oxygen, you could just walk around outside.
Why would
Now,
anybody
note,
do that?
At an altitude of 50
This is the
kilometers,
worst
there
idea.
isn't a surface to walk
Why would
on, so you'd
anybody
have
do
to
this?
bring your own. But essentially, it would feel normal. You wouldn't need a massive spacesuit like you would need on Mars, which is really interesting to think about.
Trying to
So
remember
let's
his name.
summarize.
I talked to
If
him
NASA
online
were to
from
send
G+.
astronauts to Mars versus
That's cool,
Venus,
man.
what would the trips
What's
look
G+?
like? And I say NASA specifically
Google
because
Plus?
if it was a company like SpaceX, it might not be a
That's
round
cool,
trip
man. I'm
mission.
gonna pull it up
But
after I'll
NASA
find
has
a video of
mentioned
it.
time and time again that they would want to send a round trip mission if they were to go to another planet. So let's figure out what this comparison looks like. First of all, if NASA was to send astronauts to Venus, the entire trip would take around a year and a half, whereas if NASA were to send astronauts to Mars, it would take 3 years. Getting to the planet would take 3 months to go to Venus,
Venus
and 9 months to
sucks,
go to
though.
Mars. So already it's taking less time to get
Venus
there.
really sucks.
Astronauts would be exposed to less radiation
Why would
on
anybody
Venus,
go to Venus?
and they would be able to float around on a skyship. Whereas if they were on Mars,
that.
they would be able to walk around on the surface
Yeah.
of the planet.
like
So
normal.
ultimately, you could
Like
see
normal
how
human
Venus
beings.
could help reduce some of the health risks, a shorter mission, help NASA understand how they can operate
Why?
astronauts
What's his
on
pitch?
another
Why
planet.
why does
But
he
at the
want to
same
fucking
time,
fly
on
around
Mars,
like an
there's the
asshole?
major advantage of being able to
Wearing
explore
a
the
hot
surface
suit.
directly, rather than flying around on
I'm
an
not
airship.
convinced.
Now, the last
I don't
thing
know
that
why
we can mention is
anyone's-
what about the far future?
Why is he
colonizing
convinced?
either
Like,
one of these planets. And this is where I want to
bullshit.
leave it off to you. Would you rather live in a geodesic structure on the surface of Mars or in a cloud city-like environment on Venus?
course
Let me know
Mars.
in the comments below. If you'd like to learn
100%
more about the
Mars.
future
Are you
of
kidding
space
me?
exploration and discoveries that are happening on other planets,
spaceship?
consider subscribing to this channel.
Kill myself.
If you enjoyed this video, please leave a like. But with all that being
I've
said,
been talking about this
thank
Venus
you for
man I've seen
watching,
for at
and I
least 10
hope to
plus
see
years.
you in the next one.
Really? That's not really my thing, man. I need to like go outside, walk around, you know, like that's retarded. No, thank you. But Anton said
With a
it,
lot of attention focused.
so I don't know why he said forget Mars. Should I search Mars? I don't want to like. It's bullshit. It's bullshit. We have to. Go for it, man. We gotta colonize. We gotta start colonizing, dude. Gotta colonize the moon. I know you're more environmentally knowledgeable.
Elon Musk's mission
No,
to
man,
Mars
no.
might sound like a fictional
all that
Appreciate it, man.
evaporated. Then get all the water evaporated.
You're on the
It's
King's
still
Club
not
too.
enough
That's just a
to make a
tornado.
big difference in the
You're on
greenhouse
that too,
trapping
man.
of Mars.
Take it easy, homie.
So
Thanks
if
for
we
saying
want
hey,
to
man. Thanks for
warm
the tip,
the planet,
Anton. I had
you
just
gotta
seen a video on Anton.
BYO.
That's jokes.
BYOGHG.
We'll be watching more.
Bring
He
your own
posted a video
greenhouse
today.
gas?
BYOGHG.
I think we could do that.
You think we could do that?
You know,
All right.
I mean,
See you, man.
methane. We can bring
Methane. Oh,
we
methane's another greenhouse gas.
We can bring some methane.
How are you going to do that?
Well, there's just eat a
How
lot of
y'all
chili.
gonna do that?
Meat and beans.
Jesus
Planet,
Christ.
right?
Focus it
Fucking
down on the.
retarded. This guy is a fucking retard. Jesus fucking Christ. What, he's the other guy? He's terrible. God, the other guy is terrible. I can't watch a minute of that other guy. This guy?
Let's consider a gravitational slingshot. What is that? Well,
once in a while, people like to send spacecrafts out into the solar system, particularly the outer solar system, to explore what's going on there. And because we can't on Earth give enough speed to these little spacecrafts, we need the big planets around us to help us a little. And so we can consider a large planet like Jupiter or Saturn. Here we have Saturn. And if we have a little spacecraft and we make it fly by close, then what actually happens is it will, due to the gravitational attraction of Saturn, acquire a kick in velocity, and that is a gravitational slingshot. So let's look at that. So our little spacecraft comes in with an initial velocity, and Saturn, of course, also has a velocity. And once it has passed, our little spacecraft will have a final velocity. And in order to calculate what this final velocity is going to be, what the increase in speed is going to be, we need the concept of relative velocity. And for that, we need to first consider some initial state. So we have the relative velocity initially, and that is the difference between those two velocities, between the spacecraft and Saturn. And what becomes very important here is that we look at the coordinate system and keep that in mind, otherwise we're going to get a few sign house. So the initial velocity of the spacecraft goes in the i-hat direction, and the velocity, the relative velocity is of course a difference, so minus the velocity of Saturn, but that one goes in the minus i-hat direction. And then we have the final state. So the final relative. And here we have the final velocity of the spacecraft now going in the minus i-hat direction, minus the velocity of Saturn that also goes in the minus i-hat direction. Now there's one thing that we need to consider, which is this velocity of Saturn. This one actually is, of course, here the initial velocity of Saturn, and this one is the final one. But because the mass of Saturn is so much larger than the mass of the spacecraft, we can actually set the initial velocity of Saturn to the final velocity of Saturn. So we can turn this, we can take this away here again.
Okay.
And just,
Assuming that it has zero effect on Saturn,
velocity
right?
of Saturn.
Which it won't.
Okay, good. There's one more thing that we need in order to solve this, because we need to know how the relative velocities are actually related. And the energy momentum law helps us there, because that gives us that the initial relative velocity equals minus the final relative velocity. Okay, so we can plug that in now. What do we have here for the initial velocity? We have VI minus twice gives us a plus the Saturn velocity, and that equals minus minus gives us a plus the final velocity of the spacecraft. And then we have three minuses here, so that gives us a minus the Saturn velocity. And we know from the problem that the initial velocity here of the spacecraft was actually given at
We have
three
it.
Saturn velocities. So we can tally this up now. We have 3. We have 3 plus 1 is 4, and we'll put this over on the other side. That gives us 5. 5 Saturn velocities equals our final velocity. So that's quite a good gain, I would say. And it nicely illustrates why big planets like Jupiter and Saturn are really, really helpful for the exploration of the solar system. And that is actually how the New Horizons mission made it out to Pluto, all the way out there.
Wow.
A few billion kilometers from us is a small 478 kilogram probe hurtling through the Kuiper Belt at over 14 kilometers per second. And on July 14, 2015, it passed within 12,600 kilometers of the surface of everyone's favorite dwarf planet, Pluto, just 9 years, 5 months, and 25 days after launch, which means it got there pretty darn fast.
3, 2, 1. We have ignition and lift.
Hello, it's Scott Manley here, and today I would like to talk about orbital mechanics in Kerbal Space Program. Specifically, I want to talk about gravity assist, because of course we just had the Osiris Rex spacecraft
the big
fly past the
elephant.
Earth and do a maneuver.
What's up, man?
Which,
How you
is
doing,
kind
buddy?
of familiar and yet different.
How you
if
doing,
you
my
know
man?
what you're looking for. So gravity assists are
hear from
a
you, dude.
standard tool of astronavigation that we find these days.
How you doing,
I
buddy?
mean, they kind of came to prominence really with the Voyager
shitting, hey,
probes,
man.
but you know they were used for a long time. For example, the early Luna 3 spacecraft used a gravity assist with respect to the moon to make sure it ended up in a suitable orbit to relay the science back to the Earth. Now, a gravity assist is, of course, what happens when you fly past a planet and
Chilling, how's
it
work?
let
It's
its
okay.
gravity affect
It's okay, man.
the orbit of the spacecraft. And in this case, you see I'm going from a lower energy orbit.
No, it's going okay.
And we
I am
fly
lucky to be
past,
working still, so...
Eve here. Now we're going to fly past. We come in almost radial.
How you
with
doing,
respect
dude?
to Eve in this case. And it
I got a lot to
very
do in
slightly
the
changes
system.
the
I got to
orbit,
change a lot
And then as we leave,
in the computer
we
system.
now find ourselves on
So,
this much higher energy
assignments to
orbit. So
do,
we
you
have
know, but
gained energy
that's okay.
by flying past Eve. And the real key to this is this hyperbolic encounter. Now, many people look at gravity assists and they think in terms of energy being gained. Now, it's important to realize that there is energy being gained or lost, but that is with respect to the sun. Inside this encounter with the planet, it's important to realize this is just a hyperbolic orbit, right? That means an orbit with an eccentricity which is way greater than 1. And what happens is, of course, you start here with a specific velocity, this is 3206, and as you fall down to periaps, you gain a little velocity because of gravity. We've gained almost a kilometer per second. And then as we warp
You got
travel back
his?
out, we lose
You
all
got
that energy.
this?
And we
Yeah, I
essentially
guess
enter
what, the
the
worst?
sphere of influence and leave the sphere of influence with exactly the same velocity with respect to
Yeah,
the planet.
for
Right?
sure.
In the planet's reference frame, we have just done a simple Keplerian
It's
orbit,
okay. I
and
got
the
a
laws
I
of
got a
conservation
like a
of
week
energy
or
mean we must
two
enter and leave with
deadline,
exactly
but
the
it's
same
just
velocity.
like
But you'll notice that the direction changed, and that
pressure's
is where
on. You know what I
magic
mean?
happens.
I got a 2-week
So I gave up
deadline.
trying to make it clear in Kerbal Space Program and decided to use the magic of Microsoft Paint. So yeah, this is a very simple diagram. Now, many of you will immediately get confused because the coordinate system is backwards, and that's because if you look down on the planetary system of the Earth or Kerbin from the North Pole, then the planets move anti-clockwise. So if we imagine a space probe moving outwards past a planet, a space probe which has a certain velocity, in this case I gave both objects a velocity of 1, and I said that it's moving at an angle of A relative to the planet, you can figure out the X and Y components of the orbit. Now, of course, then you subtract out the velocity of the planet, which has velocity of X equals 1 and the velocity of Y is 0. That gives you the
Yo,
relative velocity
thanks
as
for
0.765. See, that's super easy.
hanging
Now, from
in,
there,
big elephant.
you can either deflect it, say, all the way forwards, right? So you're basically taking the relative velocity in the frame of reference of the planet and now making sure it goes all the way along the orbit. And guess what? You end up with a maximum velocity, or perfect assist velocity of 1.765. And that is actually above escape velocity, because escape velocity is roughly 40% bigger than the orbital velocity. Similarly, if you take that same encounter geometry and instead have it come around the other side of the planet and slow down as much as possible, then it will end up in an orbit that will be its apoaps, and its minimum velocity with respect to the sun will be 0.235. So you've essentially slowed the orbit down. Now that we've cleared that up, I want to talk about Osiris Rex. Now, it actually does something really quite fascinating, because when it launched from Earth, it actually launched towards the sun, and it launched onto a shorter period orbit initially. Its semi-major axis was something like 0.97. Now, that's interesting because Bennu is actually on a longer period orbit. So to the uneducated eye, this looked like they had launched the spacecraft to nowhere. But then in December 2016, after a few months in orbit at perihelion, it made a 500 meter per second burn, which basically accelerated its orbit, raised its aphelion, and brought it back to an encounter with Earth in September 22nd, 2017. And here it came back and flew over the South Pole. And in doing so, it got a gravity assist, lifting it up into the 6-degree orbit plane, which Bennu is orbiting in. Now, this extra trip around the sun added essentially a whole year to its outbound trip, but there was good reason for it. By using that 500 meters per second burn, it meant that when it came back to the Earth, it was actually traveling about 1 kilometer per second faster with respect to the Earth, so that when it got its orbit deflected, it was like it had gained 1 kilometer per second of delta V that it couldn't have got originally at launch. If you remember, Osiris Rex launched using only a single solid rocket booster attached to the side of its Atlas V. They could have gone directly to a Bennu transfer orbit, I don't doubt, but they would have needed more of those expensive bolt-on boosters or possibly less spacecraft so they could get more delta V. It is important to realize that if you leave Earth at a certain velocity and then you swing around the sun and then come back to Earth without having encountered any other objects, without having performed any deep space maneuvers, you will actually arrive back at Earth at exactly the same velocity because the Earth's eccentricity is pretty low. So that deep space maneuver is essential to make sure that they can take advantage of the Earth's gravity. You could go from Earth to Venus and back to Earth and get gravity assist that way, but instead they elected to perform a deep space maneuver. They did about 500 meters per second, and I think the ultimate gain when they included the gravity of the Earth, it turned out to be about 1 kilometer per second extra. So that's like a solid gain thanks to the magic of mathematics. Now, another really important factor when computing gravity assist is that the amount of turn, the amount of deflection you can get by flying close to a body depends upon the mass of the body, it depends upon the speed at which you are going. And there is a point at which when you get close to the body in question, you cannot turn anymore because you will end up hitting the object. Here you can see that my apoapse with respect to the sun is going higher and higher, but my periapse required to get the curve is getting lower and lower, and at some point I'm essentially flying into Eve instead. Now, if you treat Eve as a point mass with no limits on how close you can get, then sure, you can get gravity assist that would take me almost all the way out to Joule from this particular orbit, but of course those would actually fly through the planet, so they're not actually very useful. Perhaps if you were, say, some weakly interacting massive particle that was doing this, that would work. You could just phase through solid matter and not worry about it, but unfortunately spaceships, at least in my experience, don't tend to fly through planets intact. So the actual mathematics for the hyperbolic orbit are super trivial. I mean, yeah, there's a lot of important stuff you can look at, but these are the numbers that you actually really care about. So if you're coming in from infinity, right, you have something called the impact parameter and the hyperbolic excess velocity. That is, the velocity you have just before you enter the sphere of influence, and the impact parameter is how far you would miss the target if it didn't have any gravitational force pulling you in. So you take these two numbers, this is v and b. Now, you can compute the semi-major axis, even though it's a hyperbolic orbit, you can compute this value, it's minus gm, m of course being the mass of the body, divided by v squared. Like, that's basically the same thing that you would get, but it's negative, right, for a regular orbit, right? Now, the eccentricity, as you know, always has to be greater than 1 for a hyperbolic orbit, and it's simple. It's the square root of 1 plus b squared over a squared. Now, of course, b is the impact parameter, a is the semi-major axis, and you get this number. And then once you have the eccentricity and the semi-major axis, you can flip that around and get the periapse distance to figure out how close it's going to be, therefore knowing if you're going to smash into the planet or not. And also, given the eccentricity, you can figure out what's called the asymptote angle. That's basically if you project the orbits back to infinity and you measure the angle between the incoming and the outgoing orbit, then that's your asymptote angle, and that's the arc cosine of minus 1 over e. Or more importantly, what you're probably concerned about is how much is the orbit deflected, and that's 2 times the arc sine, or the inverse sine, of 1 over the eccentricity. See, this is all pretty simple, and of course you can flip this around and say, if I need a deflection angle of a certain amount, can I do it for a planet of mass m, or will I end up smashing into the ground trying to get so close? So yeah, this is just a very basic lesson to try and give you the mathematics, the idea behind the geometry, so you can understand what's really going on. Again, the important thing to realize is that once you're in a specific reference frame, you're not gaining or losing energy. You know, energy is conserved. It's the rotation of the vector, it's the transformation between one coordinate frame and the other that actually makes the gravity assist mathematics actually work. Of course, it goes without saying that in the real universe as well, that the gravity assist is a mutual experience. Because your spacecraft is flying by Jupiter and getting a huge boost to its velocity, Jupiter is also being tugged on by the gravity of the spacecraft, slowing Jupiter down
deep.
ever so much.
I know, man.
It's not like we would notice Jupiter slowing down, but I tell you what we'd notice,
Really
the laws of
impressive.
physics, because in this universe we respect the conservation of energy and momentum.
They can
I'm Scott Manley.
do that,
Fly
you
safe.
know? They use... Like, let me show you the Voyager... Isn't that incredible? It's so spectacular. That was so spectacular. Alright, yeah, that's a pretty good video. Let's see how far. I wonder too. When was this made though? Because we have new information. 2019.
In 1977, the Voyager 1 space probe was launched to study the outer solar system.
Oh, I watched it at 2 times speed. That's why that video went by so fast.
41 years later, Voyager 1 is now 21 billion kilometers from Earth and traveling at 61,000 kilometers per hour.
Holy
Despite
crap.
Voyager 1 being the farthest man-made object from Earth, we are still able to communicate with the space probe on a regular basis. But how far can it go before we can no longer communicate?
Yeah, that's nuts. Yeah, man.
To answer this, we need to know how Voyager 1 receives and transmits data
That
from
was crazy.
21 billion kilometers away.
Those are like the
A 20
smartest
kilowatt
some
signal
of the
is
smartest
transmitted
humans.
from Earth to Voyager 1 using radio waves. It
Doing
takes
their,
almost
like,
20 hours for the
calculations.
signal to reach the space probe, where its sensitive antenna picks up the signal. For comparison, it takes the rovers on Mars an average of just 15 minutes to send messages back to Earth. Voyager starts sending data back to Earth using a 20-watt signal. As it travels through space, the signal strength weakens, and by the time it reaches Earth, the signal is barely detectable.
Whoa.
In order to communicate with objects that are this far away, it doesn't really matter how strong the signal is, as long as you have a receiver that is sensitive enough to pick it up.
Wow.
NASA uses the Deep Space Network, which consists of 3 antenna
Doesn't matter how
complexes
powerful
equally
the
spaced
signal.
around the Earth.
What matters is
Each
the
complex
instrument of
has a huge 70-meter antenna,
recognition.
along with multiple 34-meter antennae, which can be combined to pick up signals that are thousands of
Yo,
times weaker
DJ.
than
Oh,
your
that's
standard
DJ
FM
Farm Boy
radio
saying this
signal.
shit is deep. Yo,
The
what's
Deep
up,
Space
Farm Boy?
Network spends several hours
Some
each
nerdiest
day
humans.
listening to
By the way,
faint
shave 3
signals from
seconds off
Voyager
my
1.
silo agent.
And
Yo, are
so
you
far,
serious?
It continues
Hell
to talk
yeah.
back to us. Since our methods of detecting signals has improved drastically
man.
over the past 50 years,
I
there isn't really a
inspired you.
limit
Get
on
out of
how
here. Come
far we
on.
can communicate
It's
with
Kratos
objects in
and
space. With our current technology,
Green-oo-nay.
we could reliably communicate with objects that are many
What's
light
up,
years
Farm
away from
Boy?
us, as long as our receivers are sensitive and accurate enough to pick up the extreme.
Sorry, man. I saw the chat. Chat was red. I thought.
As Voyager travels farther and farther away from
I
Earth,
see 2 red
it takes
names.
longer to send and receive signals.
Hell yeah, Farm
The
Boy.
signal
Welcome,
strength
man.
also gets weaker, and data rates become slower, making it harder and harder to communicate with the spacecraft. Voyager 1 will continue on its journey indefinitely, and although there is technically no limit to how far we can communicate, our communication with Voyager 1 only has a few years left. Since Voyager 1 is nuclear powered, the electrical power weakens each day. In 1990, in order to save power, engineers turned off the spacecraft's camera after Voyager 1 took the famous pale blue dot image, which showed Earth as a tiny blue pixel
Wow.
against the darkness of space.
What?
Today, only 4 out of the 11 scientific instruments on Voyager 1 are still active. These instruments are being used to
Yo,
collect data
Miguel,
on magnetic fields, solar
When Voyager
winds,
hits that
and
fire
cosmic
plasma
rays
wall,
outside
we can
our
make it
solar
messed
system.
up. Yo, exactly.
In around
Precisely,
8 years,
man.
Voyager 1 will completely run out of power and will no longer be able to keep its
See,
instruments
we
going.
know. We're in the know now.
Scientists will continue to communicate with the space probe and receive the important information it gathers until it eventually sends its last bit of data and disappears silently into space,
Let's,
never to be heard from ever again. So
yeah, this
although
video's
the
from
end
January
is near
5th,
for the
2019.
Voyager space probes, we can appreciate the incredible journey they have been on and the valuable science they have taught us. Thank you to the Primal Space patrons who helped to write and research each video. If you would like to contribute to Primal Space, please visit patreon.com/primalspace, where we will be doing a giveaway of a Saturn V Lego set once we reach 50 patrons. So make sure you're subscribed so you can join in the discussion as we continue to learn more about all things space.
The images in this video are all real, captured by NASA's Mars rovers, directly from the surface of the planet. This is the first time Martian footage has been rendered in stunning 4K resolution. So sit back, relax, and enjoy this journey across the surface of another world. The team at NASA has given Mars informal place names, which you will see on the screen in the bottom left corner. The footage was mainly captured by the 3 most successful rovers: Spirit, Opportunity, and Curiosity.
Wow. Look at that. That's incredible.
The cameras on board
Look at that.
the
Fuck Venus, man. So spectacular.
This image is the largest mosaic ever put together and was made from over 1,000 images taken by Curiosity between November 24th and December 1st, 2019. It contains 1.8 billion pixels. As we zoom in, the quality does not diminish. At this zoom level, what you are seeing is exactly 4K quality. The rover was exploring the area named Glentorridon, which was theorized to contain large amounts of clay. Clay found on Mars signals the presence of water in the past. At this point in 2020, the NASA rovers have found irrefutable evidence that Mars was once a watery planet.
Amazing. It's so amazing.
You may be wondering why the sky color varies from image to image. The true color of Mars is reddish and hazy. In some images, however, the sky will appear blue and bright like on Earth. This is due to the recoloring of images done by NASA in order to aid geologists identifying rock formations. This technique also produces a much clearer picture, so we can see Mars in much greater detail. Curiosity is the only rover still active on Mars. The previous two rovers, Spirit and Opportunity, unfortunately succumbed to the Martian environment. They were launched around the same time, landing on opposite sides of the planet. Twin rovers, they are considered one of NASA's most successful missions. Spirit became trapped in a sand dune and lost the ability to charge its solar panels after 6 years of service. Opportunity outlived Spirit, roaming Mars for 14 years and making astounding discoveries. Opportunity was lost in 2019 after experiencing a massive dust storm and essentially freezing to death. NASA's newest rover, Perseverance, is scheduled to land in 2021. It will deploy a small helicopter called Ingenuity. Ingenuity will scout the path ahead, warning the team at NASA about any sand traps awaiting the rover. Flying on Mars is no easy feat. With an atmosphere much thinner than Earth's, its blades will reach up to 2,400 revolutions per minute. That's 40 spins every second. Most helicopters on Earth operate at just 500 revolutions per minute, which is just over 8 spins per second. Is currently available for interplanetary flight. It has already propelled Insight and Curiosity to Mars. So what is planned? Human curiosity. We have planted feet on the moon, so Mars seems like the next logical destination for a manned mission. Distance that it glows like the surface of the sun. Hitting it, the parachute will only slow it down to 200 miles per hour. Nowhere near slow enough to land. There is no choice but to detach and cover the remaining distance with retro booster assist. The next issue is that the rockets can't be used all the way to the ground, as they will kick up dust, covering the rover and damaging mechanisms and instruments. This problem is solved by using the sky crane maneuver. 20 meters above the surface, the rover is lowered below the lander on a tether that gently deposits its wheels onto the surface. The bridle is then cut away and the lander flies away to a safe distance to avoid landing near or on top of the rover. Once on the ground, the team at NASA can breathe a sigh of relief. The Jezero crater was chosen by NASA as the landing site for the Perseverance rover. The topography of the area looks amazingly similar to the structure of the Mississippi River Delta found on Earth. The rationale is that if water is essential for life, then an ancient river system would be the ideal place to look. The theory is that 3.5 billion years ago, river channels spilled over the crater wall and formed an immense lake within the meteor impact crater. There is some evidence that water carried clay minerals from the surrounding area into the crater lake. Hypothetically, life could have lived in Jezero crater during times of liquid water, and the sediments in the lake bed could be a source of their remains. After all, clay only forms in the presence of liquid water. Perseverance will use a similar process for entry, descent, and landing as Curiosity. However, improvements have been made to land the Perseverance closer to its prime specific target than any rover before it. As you saw with the Curiosity descent, it's already an extremely hard task to land on Mars, let alone within 10 kilometers of the primary region of interest. Medley 2 instruments will take recordings of temperature and pressure encountered by the heat shield and afterbody in the hope that the process can be further refined and made safe for future missions. Cameras and microphones will also help engineers understand the physics involved throughout the landing process, recording the deployment of the chute, detachment of modules, firing of the rockets, and the tether process as it unfolds for the first time. The added benefit is that the people looking on
might them, and you would just drive right off the ocean onto the land. Here's another one. Of course, everyone would just be floating on the water. Exercise in extending what you already know, but not inventing something completely new for those in the 19th century. That has got to be the most boneheaded comment ever printed in a newspaper editorial. You think if the two guys who invented airplanes can't get it right, what hope do the rest of us have? Here's another one. No flying machine will ever fly from New York to Paris. This is a trend that will continue up until 1957. The trend is there is some advance and people constrain that advance. So this quote came out after we knew how to fly. Now they're saying we'll never fly to Paris. Who said this? Orville Wright, 1908. How about this one? Landing and moving around on the moon offers so many serious problems for human beings that it may take science another 200 years to lick them. Science Digest, August 1948. It did not take 200 years after this. It took how long? 20 years, 21 years. So these are people who should know better. This is a magazine that thinks about science. Technology was surely advanced then. So what was missing? Let's keep going. Man will never reach the moon, regardless of all future scientific advances. Radio pioneer Lee DeForest. What's significant about this is that it's on February 1957. This is 7 months before Sputnik. 9 months before Sputnik. Launched October 4th, 1957. The moment that happened, the instant that happened, all of this changed. All of a sudden, the technology became real. The ambitions became real. And then people went back into the future predicting business, but then they began to over-predict. It happened basically overnight. A manned lunar base will be in existence by 1986. Who says that? The Futurist, 1967. The Apollo program is already in progress. So we know space is within access to our technologies. But we're assuming that we'll continue at that rate. Sorry, I didn't finish the quotes on the other side. We assumed that what was in progress would continue unabated. And that assumption was based on deeply false premises. Let me not use the word false, I'll be more severe and say deeply delusional premises. A premise that I will attempt half of this talk to convince you of. How about this? I'm convinced that before the year 2000 is over, the first child will have been born on the moon. Who said that? Wernher von Braun, the guy who invented the Saturn V rocket. So people are, again, thinking that the pace that had been put into play was something natural for the human spirit, the human DNA. What else were we predicting for the year 2000? By the year 2000, 50,000 people will be living and working in space. 50,000. I checked. In the year 2000, there were 3 people living and working in space on the International Space Station. Mixed in with this is also some foggy memory, particularly on my side of the ocean. Okay? We, in America, we think of ourselves as space pioneers. It's easy to think that because we landed on the moon. It's easy to think that we were driven by a certain sort of intrinsic patriotism, an intrinsic pride. But if you unpack it, that's not what shows up. Here's a quote, "I'm not that interested in space." John Kennedy said that to the head of NASA in 1962. The man who we all associate with launching the Apollo program. This came out of his mouth. This is, whether we like it or not, a race. Everything we do ought to be tied to getting to the moon ahead of the Russians. John Kennedy to James Webb. This is not, oh, it's exploration, isn't it beautiful? It is. There was no such dialogue. Here's a bust of President Kennedy in Kennedy Space Center, Florida, and chiseled in the granite. I believe this nation should commit itself before the decade is out to put a man on the moon, return him safely to Earth. We all can hear those words. They're stirring. What they left out is the speech where that quote comes from was to a joint session of Congress 6 weeks after Yuri Gagarin came out of orbit. The United States did not have a rocket that wouldn't explode on takeoff, a human-rated rocket. So we freaked out. Does that translate in the translators? Freak out? I don't know how else to say that. That's the word. We freaked out. So what he says before this is, if we are to show the world the path of freedom over the path of tyranny, then we need. If the events of recent weeks, wouldn't even mention Yuri Gagarin's name, if the events of recent weeks are any indication of the impact of this adventure on the minds of men everywhere, then we need to show the world the path of freedom over the path of tyranny. It was a war driver. That was in the same speech where this quote was uttered. Why didn't we put that in the granite? Plenty of space to chisel in, beat the Russians. That's left out. Well, yes, we went to the moon. Yes. Yes. Yes, we did this. Driven by Cold War fear. So all the people who were not thinking Cold War fear, thinking that going to the moon was just the thing people do, when we stopped going to the moon, people cried foul. People said, we just need the charisma that Kennedy had and that'll fix everything. We just need the political will like we used to have. No, what we needed is Russians who want to go to the moon ahead of us. There was a side benefit. This photo, Apollo 8. This is the 50th anniversary this year of that photo, December. Apollo 8 goes to the moon, orbits 15 times, does not land. It is the first time we leave Earth for another destination, ever. In some ways, this is more significant than Apollo 11. No one had left Earth before. Yeah, we go into orbit. People like to think of that as leaving Earth, but not really. In a schoolroom globe, this International Space Station is orbiting half a centimeter above the globe. Happens. 1970, Earth Day is established. Why didn't we establish that in 1960 or 19? Not yet fully understood by the public. This is really hard to get money for. But you know what's not hard to get money for? I'll tell you. Here it is. Apollo program, initiated out of fear of the Russians. The Manhattan Project, huge diversion of funds in the middle of the Second World War by the United States with an international team of scientists. The Great Wall of China, a huge undertaking. The interstate system in the United States, it's just roads, of course. However, the interstate system is roads built to a specification established by Eisenhower after he saw the Autobahn in Germany in the Second World War. The Autobahn did not wash out in the rain. It supported troop movements and tanks. And he said, I want one of those. In came the interstate system, $100 billion. In fact, the interstate system cost the same as the Apollo program, motivated by not wanting to die, moving material and personnel around. What's number two? This is not as common today, used to be common, praise of deity or royalty. From that, you get the pyramids, and you get Versailles, you get like cathedral building in Europe as an activity. Huge investments in financial and physical capital. Today, royalty is not as powerful over nations as it was 300, 400, 500 years ago. So you don't see this today so much. The third, and another obvious one, but it's a total of three, promise of economic return. There you get Columbus and Magellan and Lewis and Clark. There's no end of this list. So what this comes down to is, I don't want to die, and I don't want to die poor. That will invest in practically anything. Notice on this list is not, let's explore, let's do this for science, let's do this because it's in our DNA. You could make that argument, and you could fund below a certain radar level a project, depending on the wealth of your nation. $1 billion here, $1 billion there, depending on the wealth of your nation. You could do projects where this is not relevant. But once the price starts getting higher, you're up against people's personal rejection of what might look like the activity of others for their own gain. Whereas everybody benefits if the nation sees an economic return or if you don't die. So these three forces, war, royalty, economics, are powerful. So I've used this to judge whether anything will ever happen. Are we going to put humans on Mars? Only if somebody judges that you have to do it, otherwise you would die. Kings are not going to do it anymore, or somebody's going to make a buck. That's my cynicism that I'm bringing to this conference, based on the history of human conduct. Predicting the future, another example of how hard it is to predict the future, Collier's magazine had a now famous series of articles on our future in space. This is early. This is before Sputnik, before anybody launched anything. But we had the science. We had some of the engineering. And we had the artists. In a series of conferences at the Hayden Planetarium in New York City, a series of articles came out. And people were delighted. The world's first spacesuit. How and where we'll use it. This is a level of enthusiasm that is building. And there's a whole discussion about the physiology of going into space and the challenges. And it's on the right-hand side, meteorites, cosmic rays, weightlessness, glare, disorientation, boredom, irritability, and fatigue. Those last three would affect us even if we're not in space. I don't know why they put it up there. That's why they would list that as a priority. So here's one that will matter if you want to have settlements. They're thinking about this. Who owns? Had to ask him. He was on my television show, Star Talk. This is Baz Luhrmann. This is my office. That's an actual Saturn V rocket off his left shoulder. Well, I mean a model of the Saturn V. This is 2 minutes. Asteroids, the resources of the solar system. While you're mining it, maybe there's an asteroid out there that has our name on it. We ask you, could you please deflect that for us? And the governments get together and pay for the company that's already mining it to deflect it. Water in space costs $10,000 a pound. Sorry, I said pounds. To put into orbit. If you get it from a comet for $5,000 a pound or $1,000 a pound, that's a business model. Surely vacations, Mars, Moon, and beyond. Again, I don't see settlements so much. There are companies ready to do this. Planetary Resources, this is their landing page on the internet. And you scroll down to sustain life in space. So if you do set up a Disneyland on Mars, it needs supplies. So would you bring supplies from Earth? Not if you can get supplies from space and go from space to space. That's cheaper than launching something from Earth. So they want to control resources in space. They're going to have the first trillionaires if they pull this off. So 16,000 near-Earth asteroids, rich in resources, 2 trillion tons of water, 95% reduction in cost if you go space to space. They've already thought this through. It has a board. You know what else is on asteroids? Rare earth metals. All right? These are the full range of rare earth metals off the periodic table. Rare earth metals are not so rare on Earth, except they're hard to get to and they're not everywhere. So if you can get an asteroid that has plentiful supplies of these, our modern technology needs these to function. These are key components of our batteries, our cell phones, our communication devices. Not only those asteroids have precious metals, gold, silver, platinum group elements, and of course they have water. Plus we've been to them before. Governments paid missions to visit asteroids. This is asteroid Ida. This is Galileo approaching Ida. It did not collide. That's actual footage as it got closer. It's not just a zoom in. This is Ida. We've been to asteroids. We understand them. We've even landed on comets. But perhaps the most important motivation, let's get back to the war motivation, defense. I don't want war to be a reason for anything, so let's rethink that. Maybe there's a security problem that we face as a world body. Let me remind you that the universe, there are many ways Earth wants to kill you. Earthquakes, tsunamis, this sort of thing. The universe wants to kill you too. These will happen, but they're not as common. You know, you want to avoid black holes at all costs, yes. Solar storms are bad, but what's much more real are impacts. And we have had extinction level impacts in the past. So you could colonize other planets to mitigate this, but again, you have humans on 2 planets and one is about to go extinct. You're just going to sit there and say, goodbye, glad we're not there. No, you're going to deflect it, especially if you already have people who know how to mine them. So that's not worried about. But there could be one, you didn't want to be on Earth when that happened. This is a real crater in Arizona. It's 1.5 kilometers across, 1.5 kilometers across. It can sink a 60-story building in the middle. We've been hit before, we will be hit again. You want a space program and you want to fund it? Say, we don't want to die. We don't want to go extinct. How's that for a defense program? You want evidence that this is real? Anyone here from Russia? Any Russians in the room? Russia, Chelyabinsk, the town, February 15th, 2013. Forward-facing dashboard camera. You see a little dot of light in the middle? Watch this. That's full video and sound in the car. Now, I'd always been told that the Russians are stoic people. If I were driving that car, I would say, holy shit! The car would have at least and I know what I'm looking at, right? I would have at least reacted in some way. Just to show you that we're in a shooting gallery, 17 meter, 10,000 tons, 40,000 miles per hour. The energy of 25 Hiroshima bombs. But it exploded 20 miles up. Again, apologize for the miles. 30 kilometers up. So a lot of the energy was diluted. But what it did, no one died. But the blast wave collapsed walls, shattered windows. The injuries were glass shattered glass. And there's a time delay. That's how so many people got injured. They're sitting there eating breakfast, a bright light comes through the window, and so I wonder what that light is. And then they walk over to the window, look out the window, then the blast wave hits. The time delay between the light and the sound. Here's an example of video in the town of Chelyabinsk. So that's the smoke that went just past above them. So here it is, amateur video after it passed over.
И сгорел там, да? Ну.
That's the shock wave. But there's a couple more.
Ты
Just
думаешь,
watch.
может, спутник там уже же падал, а не
And we can laugh because no one died, but this is a compilation of the blast videos. And this is 17-meter asteroid. That's all. 17 meters, size of the stage. Like, where did he come from, right? Warehouse structures are not reinforced typically, so they were the most susceptible to this blast wave.
Ну что, ребята, счастливого вам, счастья, удачи.
So what I like about this is the kids didn't run out of the room. It was like, oh gee, what was that? Let me keep looking. Let me end with just a reflection on the value of even saying you want to go into space and doing so, even if the projects are not expensive or you're not colonizing yet. Because doing so can have an effect to invent something for the 60 and 1970. It's been dropping ever since. I'm old enough to remember this. It was all about the future. Just the feeling that was. I didn't even know I wanted to be an astrophysicist yet, but I was being imprinted. This is the Unisphere in World's Fair in New York City with 3 rings around it, evocative of the 3 orbits of John Glenn. It was all about the future. Then we started
-6 single-celled organisms. There we humans are, 2 meters. The Earth, 10 to the 5 meters. Solar system, 10 to the 13. Galaxy and on. Only have direct access to a small piece of it. One more axis to look at is the axis of speed. So we humans, we walk around the world at certain ordinary everyday speeds. Sometimes you go into airplanes, but there's a huge range of speeds out there. The growth of human hair, that's pretty small. Human speed, typically, space shuttle, 10 to the 3 meters per second. Speed of light, that's a number that's going to come up a lot in our discussion, 10 to the 8 or so meters per second. The point is, in this spectrum of all possibilities, in length, in mass, and also in speed, we humans occupy a tiny, tiny part. So our experience, the experience that has given us our intuition, is built up from a very limited sense of what is actually out there. So our intuition, which really has come in some sense from evolution, right? So we evolved out there in the jungle, and our intuition got built up in order that we can survive. The survival value of understanding your environment is what that distance is a measure that has to do with space. That is what we are after. Okay, good. That's where we're headed. Now, that car is executing a and subtractive. You can change the speed with which an object is coming toward you by either running toward it or away from it. And remarkably, the speed that he found for electromagnetic waves, again, independent of whether they have a very long wavelength or if, for instance, they have a much shorter wavelength, like this fella coming in here, he found in the equations that the speed of those electromagnetic disturbances would always be equal to a particular number, and that number turned out to be 671 million miles per hour, or 300 million meters per second. So this was a stunning insight. And again, if you haven't studied electromagnetism, it doesn't matter. All that matters here is that Maxwell had these equations, and from the equations out came, from a calculation, a speed that was equal to the speed of light. What was Maxwell to conclude? Well, naturally, he said, if the speed of the electromagnetic disturbances is equal to the speed of light, then light itself must be an electromagnetic disturbance. It must be an electromagnetic wave. That was a great step forward. Now we had an understanding of what light actually is. But even with the progress that that represented, it still raised a profound mystery. And that mystery is this. As we described before, whenever you talk about speed, you need to say an object has this speed relative to that object. You need to state things in that manner for speed to even have any meaning, right? But when it comes to the equations that Maxwell was studying, they didn't specify what speed 671 million miles per hour was relative to, right? So if you have sound waves, the speed of sound is relative to the still air. If you've got water waves, the speed of the water wave is relative to the still water. What was the thing relative to the speed of light was being calculated? Nothing seemed apparent, so physicists dealt with this mystery by making up an answer. They said maybe there is something called the ether filling space, and when you talk about the speed of light, you're talking about the speed of this electromagnetic wave relative to the ether. Experiments were done to try to find the ether, and to make a long story short, no evidence for the train is going along. There is a table again in one of the cars. It will have undergone a diagonal up and a diagonal down trajectory as I'm walking with the light clock. So I'll show you this in a moment, at which time on it will tick off more slowly than on a clock that is stationary. That's the key point. But we want to go further, because ultimately what we really want to do is not the duration of tick-tocks, but the elapsed time. So the elapsed time on, and I'll fill in which clock in a minute, divided by the elapsed time here, and I'll fill in the clocks right now. So if the duration of the tick-tock on a moving clock compared to the duration of tick-tock on a stationary clock, let's say this is a ratio of 5 to 1. That means that 5 times more time will elapse on the stationary clock, where the tick-tocks are faster, compared to the amount of time that elapses on the moving clock. So then this translates into the elapsed time on the stationary clock compared to the elapsed time on the moving. These are inversely related to the duration of the tick-tocks. This is equal to d over L. So again, if this length here is 5 times the length for the ball to go up and down, the ball of light to go up and down in the stationary clock, then that means the tick-tocks are happening 5 times as slow in the moving clock, which means 5 times more time will elapse on the stationary clock compared to the moving clock, because the tick-tocks are happening faster over here. So that means that we can now take the little formula that we have indicated over here and translate that into the elapsed time in the stationary clock to the elapsed time in the moving clock is the ratio of the length of that diagonal that we have over here to the length of the straight up.
Blackstone Audio presents Astrophysics for People in a Hurry by Neil deGrasse Tyson. This book is read by Neil deGrasse Tyson.
For all those who are too busy to read fat books, yet nonetheless seek a conduit to the cosmos. Preface. In recent years, no more than a week goes more important than our laundry list of shared gas clouds, super duper high energy
Beneath the complexities of everyday life, the rules of our universe seem reassuringly simple.
This solid bridge supports my weight. The water flowing underneath always goes downhill. And when I throw this stone, it always flies through the air following a predictable path.
But as scientists peered deep into the tiny building blocks of matter, all such certainty vanished. They found the weird world.
Good to see all of you. You see a quote up there by Niels Bohr, one of the founding figures of quantum mechanics. Anyone who thinks they can talk about quantum mechanics without getting dizzy hasn't yet understood the first word of it. Now, why would that be? What did Niels Bohr mean by that? Well, basically he meant that we all have a good intuition for classical physics, right? And by that I mean, you know, if I was to take any little object, right, give it a catch, nice, did a one-handed catch right there, throw us a little bit further back, and we go 2 for 2. No, we're 1 for 2. They're still back in the dark age. Here we go. Give that one over there. Good. Right. It from qubit collaboration. He was a Canada researcher space-time and quantum computation, which will take us right through to the end. All right.
Pattern. But it has nothing to do with particles. It's the mathematics that you use to describe waves, water waves, or other kinds of waves.
Yeah, so can we see the animation that has a single? So this is a warm-up to the problem where we have water going through a single opening. And just tell us what we see happening here.
That's right. So you've got sort of a water wave, a wave front coming along, and then just that slit acts as a bit of a source for this rippling wave going out in a circular pattern, and you see in the double slit, right?
Present if you have a wave associated with a particle. Wave is
so I could think
that goes all the way back to Einstein. That
environment to happen, but if you do this, and then at the end, after many procedures, quantum procedures, you would construct a very carefully designed measurement, and ideally you'd want one measurement at the end, and it would be the right measurement that would give you the answer to your calculation.
And are we
And
going
this-
to we're going to reach
Yes,
this?
this was very important because factoring large numbers lies at the heart of most of our encryption schemes, the encryption of your credit cards today.
Hello wonderful person, this is Anton, and in this video we're going to be talking about the beautiful Jupiter. In one of the recent studies that I was able to discover completely by accident, we discovered that maybe, just maybe, we were not really correct about the origin of this planet. It seems that the study from University of Lund, which is in Sweden I believe, actually found out that this planet was made in an entirely different way from what we expected. So let's talk about this, and welcome to Webinar. So, our previous assumption about this planet is that it was made somewhere where it's located right now, maybe a little bit closer to the Sun. And the way that we believe Jupiter moved in our solar system, and this is by the way known as the Grand Tack theory, basically we thought that it kind of got attracted to the inner solar system and made its way closer and closer to the Sun, stopping somewhere around where Mars is located. Then, because it was so close to the other objects that were here, it influenced a lot of planets, and some of them collided with each other. And then its friend Saturn decided to pull a little bit more on its neighbor and managed to pull Jupiter all the way back to where it is located now, at a distance of just over 5 astronomical units. So that's how we believe Jupiter was made. But the only problem with this particular hypothesis is that we don't really have any actual substantial proof or really any evidence of this happening. So we're kind of left with just kind of guessing as to where Jupiter came from. But this particular study that you can find in the description below talks about something entirely different, and they kind of give us proof as well. So what they did is they actually created simulations, specifically very, very complex computer models that they ran many, many times, where they placed Jupiter in different locations around the solar system. But they weren't really interested in Jupiter. They were actually trying to figure out why Jupiter has such an unusual number of so-called Trojans. And not just an unusual number, but a different number of Trojans. Okay, so first of all, let's briefly talk about what Trojans are. You can actually see me selecting some of them, but obviously not all of them. So, first of all, Jupiter, just like every other object in the solar system, has several stable points of orbit known as the Lagrange points. There's one that's very, very popular with different spacecrafts. We actually have a bunch of them between Earth and the Sun. This is called L1. But there's also two Lagrange points, L4 and L5, that are sort of about 60 degrees, this is basically 60 degrees, in front of the orbit and 60 degrees behind. Now, this is known as the leading Trojans, and this is known as the following Trojans. And Jupiter has a lot of these asteroids that it was able to capture over the 4.5 billion years in these particular points. There's about 7,200 of them that we've discovered so far. And it just so happens that for some unusual reason, there is about 40 to 100% more of them here in front of Jupiter. To tell you what may have collided with Jupiter, let's talk about some of the more famous examples of collisions with this beautiful planet. Although maybe it actually hasn't stopped completely just yet. And by then, it captured all of these Trojans that it has today. And it just decided to conduct the experiment and find out if the modern light speed and also very thick atmosphere of the planet. Here the speed was about 48 kilometers per second. So unfortunately the probe only got to measure some of the components of the upper atmosphere. It never really got to the part where we could have potentially found life. And one of the reasons why the probe was destroyed in this way was to essentially eliminate any chance of the probe itself contaminating the moons of Jupiter. Generated a circular object here. It's most likely below all of this atmosphere. It was believed that there was something, but we've discovered that instead it has a very kind of a fuzzy mixture of layers of metallic hydrogen inside, and basically the interior of Jupiter is very irregular. There's no sphere on the inside that we thought there was. There's no any kind of iron core. the effects of the unusual magnetic field and specifically the interaction of various magnetic lines coming from inside Jupiter. So here, this is kind of reminiscent of what we might actually see on the surface of a star as well. And we know that stars get these spots only because of the magnetic effects and magnetic lines. And we know that stars get these patches and dots because of the magnetic lines and because of the magnetic field itself. And so that's the second unusual effect that was actually kind of unofficially explained. And the third discovery coming from Jupiter is coming to us straight from here, the great red spot of Jupiter. And what we've discovered is that inside of this beautiful spot, if you were to actually try to go underneath all of this surface layer and try to jump inside, what you would discover is a beautiful layer composed almost entirely of water molecules. And what's even crazier is that it's actually a lot of water. It is a tremendous amount of water. So in other words, we actually discovered a huge deposit of water inside the red spot, the great red spot of Jupiter. And what's even crazier is that it's not just any kind of water. It's water at a pressure of about 5 atmospheres inside the actual cloud that gives it enough temperature, about 0 degrees Celsius, to actually become liquid droplets of water. So there's literally a cloud of water vapor that is sort of circulating around that great red spot that could potentially also have, well, life? At least that's the official speculation coming off some of these scientists right now. If you have liquid water, you could potentially have life, and if there's actual liquid water droplets in that great red spot, we could potentially find some kind of atmospheric life. Now, maybe, maybe not. We'll see when we get there. And in a nutshell, that's basically what we've discovered in the summer of 2018 about this beautiful planet known as Jupiter. We've discovered it has unusual, very weird magnetic field. We also discovered that this magnetic field creates these unusual clouds we see on the surface, and that somewhere out there, there's actually liquid water on the inside, potentially enough to actually be viable for life. Hello wonderful person, this is Anton, and in today's video we're going to be talking about the Juno mission and our beautiful Jupiter. In 2017, Juno discovered some of the more incredible findings about this unusual planet and redefined our understanding of it. So even though Jupiter actually looks very, very incredible in Space Engine, we're probably are going to be using another application known as NASA's EYES, where we actually get to see the Juno mission and find out exactly what it discovered around the beautiful Jupiter that doesn't look as beautiful in here, unfortunately. Now, first of all, this application is totally free, so you can download and check it out.
to crowds, to a group of children at Fatima in Portugal, and there are a series of extraordinary apparitions involving tens of thousands of people. We've all heard of demons and angel experiences, and the common factor in all shamanism, everywhere in the world that it is practiced, is altered states of consciousness. If somebody claims to be a shaman and they are not entering a deeply altered state of consciousness, then I would say they're using the wrong term for themselves. That person is not a shaman, that person may be something else, but altered states of consciousness are fundamental to shamanism. The Inuit shaman, I can't even pronounce his name, Ijugarjuk, endured a grueling initiation in isolation during the depths of winter, 30 days of cold and fasting that he almost died. And towards the end of the 30 days, there came to be him a helping spirit in the shape of a woman. And while she came, he was asleep and seemed to hover in the air above him. She became his helping spirits. And so fasting and austerities and privation were the technique that this individual used to enter a
Tepe is firmly dated to 9,600 BC. It consists of a vast series of gigantic megalithic pillars, more than 70% of which are still under the ground, though revealed by ground-penetrating radar. It raises questions over the origin of civilization, since we have not anywhere in the world before found a gigantic megalithic construction dated to 11,600 years ago. And since Turkey is not very far away from here, and since I at least feel there are question marks over the Sphinx, I think it's relevant to consider the recent discovery of a gigantic megalithic site in Turkey dated to 11,600 years ago, and to wonder whether we should raise questions over the Sphinx again.
I don't think that what has been said is right. It has nothing to do with anything. In my opinion, we know the date of the Sphinx. What has been found in Turkey, I don't think, and I don't know if this is true or not. Did you ever hear about this? Make a comment.
Yes. The Turkey, it's eastern Turkey actually, to the east of Ankara, between Ankara and Van. If you look at the traditional dates for ancient Egypt and compare it with Göbekli Tepe, which dates actually from the late 11th millennium BC through the 10th millennium BC, these are two civilizations worlds apart. I wouldn't call it a civilization in the case of Göbekli Tepe. Civilization is characterized by...
The radar showed anything? Because I don't believe in radar. I have been using radar all my work. It never made me in the sky.
Well, I'm afraid the radar does show, and you're discrediting the German Archaeological Institute. And Professor Karl Schmidt, who sadly passed away a few months ago, a very sincere and decent, hard-working man, who has published his findings on which are not in dispute. Göbekli Tepe is 11,600 years old. It is a giant megalithic site. It isn't very far from Egypt. It is a relevant context, in my view. At least it should cause us to have some curiosity about some of the sites in Egypt.
If I can take a stand as a person independent of these two respected gentlemen, in my opinion, Göbekli Tepe and things or old Norwegian can't be compared. They are separated by millennia of history. It's different type of architecture, it's different type of culture, in my opinion. And of course, we can't expand on this topic any further at this moment because most of you are not familiar with the issues. But take some time in the evening, look it up on Google, and you will see if there are common points, common characteristics in between these two places. I leave it open to your judgment.
The argument about the Sphinx made by Dr. Mark Langer some years ago was that the Sphinx couldn't possibly be 12,000 years old if there was no other site, no other megalithic site anywhere in the world which was anywhere in the range of 12,000 years old. When we have a major discovery conducted by a respected archaeologist,
It's good to see you all here, and it's good to be here. And if I collapse on stage from a heart attack, don't be too surprised, because I got in at midnight last night with hours of jet lag, and I'm feeling a bit floaty at the moment. But I'll do my best. I'll do my best to keep it all together. The ancient texts from many different cultures say that it's an incredible, different world. Explanation, when I know that there were global floods at the end of the last ice age, when the whole world was flooded again and again and again. And I do believe that the flood myths from
This is Cosmographia, the Randall Carlson podcast. Welcome back, ladies and gentlemen, to Cosmographia, the Randall Carlson podcast. We are joined today by all the usual people. We got Bradley. How you doing, sir?
I'm good, man. Good to see you guys. We're back.
Yeah. Mm-hmm. Still remember it from episode 21.
Feature. Yeah, 120, 150 degrees. It's a good ways around the circle.
Right. Okay, so that was the first paper of his career. Interestingly, 1944, I believe it was, 42, 44, the last paper of his career. So he did all kinds of stuff between 1910 and his retirement in early 1940s. His first paper, Lake Missoula. His last paper was about Lake Missoula, like bookends to his career. The last paper that he wrote in the 40s was entitled Unusual Currents in Glacial Lake Missoula. Unusual. That was his way, his non-emotive way of describing what he'd discovered, which was gigantic current ripples. Well, what that led him to believe is that, wow, he'd already concluded there was this big volume, big body of water there. Now when he sees these current ripples, then he also notices that there's, along the hillsides, many of the hillsides, there's scoured rock up, and by measuring, taking repeated elevations of the top of the scouring, he was able to conclude that the high water level rose to 4,200 feet above sea level. Okay, so now when you go into the basin of the Missoula Basin, where the town of Missoula is. You go to the campus at the University of Montana there, and there's two mountains, Mount Sentinel and Mount Jumbo. Very conspicuous shorelines on those mountains, right? 4,200 feet above sea level. Now, the valley floor is about 3,000 feet above sea level. So that means that in that basin right there, you can easily figure out that the water was up, maybe it was 3,200, because the water there was about 1,000 feet deep. But now as you go to the west, and as you're going, now all of this is part of the Clark Fork River watershed that ultimately is now drains into Lake Pend Oreille, northern Idaho Panhandle. As you go west, the gradient is dropping. So by the time you get to Lake Pend Oreille, right where you get to roughly, you're in the Clark Fork Valley, you're at the border between Montana and Idaho. You're now at about 2,100 feet above sea level. The scouring on the mountainsides is 4,200 feet above sea level. So he was able to go, wait, gosh, here's the scouring on the mountainsides in the Clark Fork River Valley, and 150 miles away or so, or 100 miles away, he had found shorelines that were also 4,200 feet above sea level. Okay, so from all this, he'd been mapping this vast region where this huge body of water had accumulated and called it Lake Missoula, right? Well, in his early 40s paper, he had discovered the giant current ripples. And one of these current ripple fields was in a place called Camas Prairie. And Camas Prairie is near Flathead Lake. It's right to the west of Flathead Lake. And in Camas Prairie, there's this massive ripple train. We're going to be looking at pictures, video. Brad's got drone footage. We've been there many times. And when you look at the anatomy of these ripples, what you see is that they're composed of really coarse gravel and boulders and everything like this. It's a huge mass of material. The total ripple train itself is almost 5 miles long, and it diminishes from maximum size at the north end to where it sort of disappears at the south end, about 5 miles away. And where the current ripples are the biggest at the north end, the amplitude ranges between about 30 and 50 feet. The wavelength varies anywhere between 200 up to a maximum, I think, of about 500 feet. So when you're in one of the troughs, you don't even really see, you can't see over. It's like, you'd be standing there and these hills are like a 5-story building on each side of you. So, okay, to make a long story short, if that's even possible, J.T. Pardee discovered, he didn't discover, but he certainly elaborated on the idea and made it a scientifically accepted model, Glacial Lake Missoula. So in the I believe it was 1940, I don't remember the exact date, but James Galooly, who was one of the leading critics, organized this conference in Washington, D.C. We've talked about that, where he invited Brett to supposedly get a fair hearing for his, outrageous catastrophic flood hypothesis. But what it really was an ambush where he got a lot of people sympathetic to his side, and their goal was to essentially put an end to this giant flood heresy before people took it and said, oh, this was Noah's flood, and oh, here we are right back to biblical diluvialism again and all of that. Well, J.T. Pardee ended up at that conference, at that meeting, in that meeting room. And he was listening to the whole thing as Brett is laying out his case, making his case that the channel scablands of eastern Washington had been created by this really huge catastrophic flood. Although I think by this time, I believe Brett was already thinking there might have been 2 floods or even 3 floods, right? In any case, Pardee didn't say much. In fact, didn't say anything apparently until the end of the conference, when he leaned over to one of his colleagues and whispered to him and said, I know where Brett's flood came from. And this was where Lake Missoula, Channel Scablands come together right there. Now, geological mainstream community, which is heavily invested in the idea of uniformitarianism, the idea that whatever happened in the past, we have to explain it by reference to a modern process. Well, see, this provided the uniformitarian way out for the critics, because now what they would do is go, oh, there we go. It was a glacial ice dam. That was an outburst flood. We've seen those in Iceland. We've seen those in Alaska. We've seen them in British Columbia, where an ice dam, particularly because, by the 1940s now, the Little Ice Age has been going away for 100 years, right? Well, remember, the Little Ice Age, the planet's glaciers grew bigger, or as big or bigger than they had been in 11 or 12,000 years, right? They weren't that big, but it was the biggest the glaciers had grown throughout the entire Holocene. So that's a point to keep in mind.
Mm-hmm.
Little Ice Age. Yeah, these glaciers were big. So they started receding in the early to mid 19th century. As they receded, they created proglacial lakes. So the northern climates that were glaciated during the Little Ice Age underwent a century to 2 centuries of Jökulhlaups, which is the Icelandic term for these glacial outburst floods. Now, what seems to be happening is, because the glaciers have receded to the extent that they have, is that this episode of these semi-catastrophic floods seems to be waning, right? Because you picture 150 years ago, many of these glaciers were 3 times the size they are now, 4 times the size. So obviously, when they're melting back, they're producing copious amounts of meltwater. In some cases, like for example, if you have a trunk glacier that's melting back, and you've got a tributary glacier that's melting back, and you've got a main trunk glacier that's going to be much more massive. It's going to take longer to melt, right? Well, what'll happen? The tributary valleys melt, and they pond against the main valley trunk glacier.
That's understandable.
Yes. Now, when that main trunk valley glacier melts to a certain extent, at some point the water kind of overcomes the glacier and it can't retain it anymore. Typically the water sometimes will overtop, but usually it forces its way under. And once it gets under and starts piping, that erosional process proceeds exponentially, and boom, you have an outburst flood. The lake drains, the tunnel, the outlet will seal, right? And the water will begin accumulating again. And then maybe the next year, several years later, the process will repeat. And these are referred to as self-dumping ice-dammed lakes. And they'll go through this process until the glaciers are basically gone, right? Now, here's the thing, coming back to the breath. Because of the fact that geologists have been seeing this going on, they said, well, there's our explanation. You had glacial Lake Missoula held in by a glacial dam. The glacial dam gave way in the same fashion that we witnessed, in the last 50 years, say, of ice-dammed lakes breaking out in Alaska or, Canada, British Columbia, wherever they might have been, right? One problem, though, that seemed to have been sort of, in my mind, kind of neglected and overlooked.
You needed 600 cubic miles of water to refill the lake.
Yes, and the problem is, and we're going to show this because I've got a massive amount of really interesting information about processes and effects of modern outburst floods. Because remember the scale invariance phenomenon, we can look at smaller stuff to get the bigger picture. But when we look at the modern outburst floods, what we're going to be confronted with when we start looking at peak discharges and maximum volumes is that the amount of water for the Missoula floods is typically more than 1,000 times greater than the modern scale of outburst floods. That to me is a proportional situation. It can't just be overlooked. And it's been referenced. I'll show you some of the references I've got. We're saying, well, yeah, it's 3 orders of magnitude larger than any known outburst flood, but then they go right on And then I recall I got one paper here which says, well, it is a major extrapolation of the data. Yes, it's a very major extrapolation. Can we just go, okay, we're going to take a modern glacially dammed lake and an consequent outburst flood, scale it up by 3 orders of magnitude, and say, no problem. See, that's where I start having a problem with it.
Yeah, why are they okay with doing that, with that process, but not with just a flood that has no dam involved? You know, no ice dam. Why can't we just scale that up until it's big enough to cause the whole thing?
Well, because you have no way, and see, this is when we get back into the energy paradox we've referred to. Where's the energy come to melt that much? You got to have energy. You got to have heat to melt that much water that fast.
Right.
That's the problem.
SUVs, man.
What's that, Kyle?
No, there was a bad throwaway comment. SUVs. SUVs will do it.
Well, okay.
Cut that part out, Brad.
My theory was that, it was, all the woolly mammoths. 10 million woolly mammoths.
Oh, yeah.
Clearly.
Flatulating.
It was, there was a sudden simultaneous increase in methane expulsions.
That's right.
Which caused a rapid catastrophic global warming. So
I just want you to know that all that stuff that you just said is what I meant to say about Brett's.
Right. I knew that. That's why I was trying to help you out a little bit there.
I got nervous. I got nervous.
Well, don't worry, because we're going to recap this next week, and then you'll get to basically re-expound the entire thing that I just laid out.
All right.
In detail.
Yep. So
let's go back to Lake.
I did want to slightly, take a moment though to address Russ's question about the multiple floods.
Yeah.
Just to say that it's extremely complex. You can go to some places and there's evidence for what looks like 40 floods. You can go to other places and it looks like, they've had 90 floods. Some places it looks like 2 huge floods. So there's many different reasons for some places getting washed away and recreating the landscape, so there's not evidence of the previous floods. So, I mean, it's very complex. There's different reasons for there being different quantities of floods that have been, hypothesized.
And we will explore all those reasons for the most part.
All right.
And I the number of comments over years, not a whole bunch, but probably half a dozen comments where I think there was a recent one, and I think one of you guys forwarded to me. Somebody was saying, well, they watched one of Nick Zentner's videos, and what did he say? That blew my single flood hypothesis
out of the water.
Yeah, something like that. It blows holes in my single flood hypothesis. And I've been thinking, now wait a minute, what single flood hypothesis would that be?
Yeah,
I mean,
and he should have said blown it out of the water, because
Yeah, right. I mean, it should have. Yeah. No, clearly, it's like Brad said. It's much more complex than that. Brett's was certainly at that, but see, what then happened was that with the acceptance of the gigantic flood as a possibility, with the adaptation or the adoption of the glacial outburst flood model, it now became academically acceptable to talk about this flood, and accept the flood. Yeah. And Brett's original idea of accelerated melting of the Cordian ice sheet basically got abandoned, even by Brett's. Although I have a suspicion that even for the rest of his life, which went on for quite a few more years, like another 30 years. I mean, he was 96 when he passed away. That he might have not been fully 100% comfortable with the whole ice dam model. And maybe somewhere in the back of his mind was still trying to come up with some way to explain an accelerated melting. Okay, well now, to get it back to what we started with, was this paper that came out in 1999, right? Which was entitled Back to Brett's. Now, you see the significance of the title, Back to Brett's. Yeah. Going back to the idea that maybe that there was at least part of this flood phenomena that came from Canada, that came from British Columbia. That was the significance of that. So For me, what was so exciting was that Brad and I had this idea. We're going to go back. We got our tickets next month. A few weeks in the future, we're going to go to British Columbia and explore these places. We're going to go up the Rocky Mountain Trench. We're going to look at the Fraser River Valley. We're going to go up into the Okanagan Valley, right? July, this paper comes out. Lead author John Shaw, Jerome Lessman. I think at that point we can ask him, but I think at that point he was a graduate student. He was one of the co-authors of this paper, Back to Bratz. So here, this in the glacier did see the what did Jerome call him again? Doing. The full ice mass is there. It's bearing down on the North American continent, creating a depression. As the ice shrinks back, meltwater forms around the rim. But as the land comes up, what happens is you will have episodes where that water spills over the drainage divide because it wants to get back to the oceans. We'll see the same process at work out when we look at the channel scablands. And I think that is part of the explanation for the complexity of the flood features out there, is that there were 1 or 2, 3 smaller flows that were from residual melting and drainage, proglacial drainage that occurred because the land was uplifting. So as the land is uplifting, that water, let's see if I can do it here. Let's say this is the glacier, and as the glacier melts back, the water increases, right? But then if the land rises, then the water spills over the divide. All right. So that then contributes to this complex feature. There we go. That's a good one. That's a real good one. So there you can see this was the maximum extent of Lake Agassiz, and it was most likely, no, it was not at any given point. It was not this entire gray area, because the basin of the lake throughout a process of maybe 3,000 to 4,000 years shifted. So it went through periodic drainings as the land rose, as the ice receded, and allowed a changing series of outlets to the ocean. But I want you to look right down here at the very southern tip. You see this limb? Yeah, that comes right down there. That's the southern outlet of Glacial Lake Agassiz. And it drained into the headwaters of what is now the Minnesota River. And I've told this story about, that arrow, see that arrow, that black arrow that comes down, that is the pathway, the valley that the Minnesota River now flows in. And it was that valley that I saw in 1969 when I was at a rock concert at Eden Prairie Airport, which was built on the bluffs overlooking the Minnesota River Valley. And I got this sense of scale and variance because I could see the Minnesota River flowing down below, and I could see 3 miles, 4 miles on the other side of the valley was another set of bluffs matching the set of bluffs that I was standing on. Now, when we went back there, this was much harder to see because we went back there maybe 3-4 years ago. And of course, what had happened was there had been a lot of tree growth and vegetation growth. And apparently, maybe the place got logged over in the 30s, 20s, 30s, 40s. I don't know, because there was not that much vegetation growth and forested area looking into the valley in 1969. So the features were much more visible than they were when I made that return visit. But we stood upon that same spot where I was looking out over the valley and could see the matching bluffs, and then seeing the Minnesota River down below with a set of bluffs on either side. So that was this intimation that it was like, oh, look, this thing here is like a giant version of this thing here. Now, of course, I had no knowledge whatsoever of geology in 1969. I just had this interest in I was interested in geology. I was interested in nature, the weather, the climate, the everything. I was interested in all kinds of, I was a budding natural philosopher, right? So it was years later that I got actually challenged in one of my lectures by somebody who had a degree in geology, when I was talking about this episode where I saw this thing, and he said, no, that big valley was produced over millions of years. And I said, no, I'm pretty sure you're wrong. And he said, no, look, I've studied geology. I know that's, these things take long time to form, I don't know, but I tell you what, that motivated me to really, really, look into it. And of course, what I can now know is tell you that, oh yeah, well, that valley was created by glacial River Warren, whose peak discharge was 4,000 times greater than the modern Minnesota River. Right? I know that now. Right? But the cool thing is that flood that created glacial River Warren, 4,000 times greater than the modern Minnesota River, which ultimately drains into the Mississippi, just there by St. Paul, Minnesota, that was the southern drainage of Glacial Lake Agassiz.
So you mean to tell me that at the time you didn't look at that geologist and say, well, the paleo current indicators suggested it was a giant flood?
I didn't say that because I didn't even know the term then, paleo current indicators. Although not long after that, I did learn.
I know how you feel.
What it was. I mean, I would say that, I had a abiding interest in geology all through the 70s and a lot of observational stuff, but not hardcore study until, I tell you what triggered it was when 1980, when the reports came out that the Earth got struck by an asteroid, and that really galvanized a resurgence in my interest in these things. Mm-hmm. And that is when I would say I really started like scouring the geological literature and thinking about geology and buying books on it, reading about it. It was another decade later before I actually began taking courses on it. But yeah, that's pretty much how it started. And the idea of an asteroid impact really fired my imagination.
And that was right after Mount St. Helens too, so that definitely woke a lot of people up and said, what's going on with geology and volcanology and earth changes here? So yeah, that was right in the same year, within a few months of each other.
Yeah. Would you pull that map up again? And let's see if we can locate where Lake Hind is on there. Let's see. Okay, cool. I think we can just about see it. We've seen the southern outlet, and I'm gonna this actually in our, we want to call it a pilgrimage, where we led Graham Hancock across from Portland to Minneapolis. That was one of our last stops, was at the southern outlet of Glacial Lake Agassiz. And so I have some photographs there of some interesting features that formed. But if we go up right about where you see Manitoba, yeah, do you see Manitoba?
I'm not real clear, no.
Okay, so okay, you see,
it's been a long time since took geography.
Okay, so you see North Dakota. Can you find North Dakota? It's next to Minnesota. Yeah, that's North Dakota. Now, directly above there is Manitoba, and then, yes, that's Manitoba. And that borderline, north-south borderline, is the border between Manitoba and Saskatchewan. Okay, so if you go down right in that little corner of southwestern Manitoba, and your mouse is right now kind of on a little black smudge there, that's the area we're interested in right now. And that's the area of Lake Hind. So go ahead and close this out. And I'll go back to here. All right. Here we see I've put in a little blue polyline down here to represent Glacial Lake Hind. Pretty close. It's approximate. Yeah. A couple of the maps I've looked at weren't exactly the same. just depends on which phase of the lake we're talking about, but this is pretty close. And this was right next to Glacial Lake Agassiz, which, if you look here, the basin of Lake Winnebagosh and Winnebagosis right here, that was where the edge of Lake Agassiz was. So this was very close to Lake, and then it at some point actually drained into Lake Agassiz. So let's go through here. Here you can see up here, upper right corner, you see Lake Agassiz, and there's Lake Hind, right? And this little connection between the two. And this one is actually showing Lake Hind crossing a little bit into North Dakota. We'll skip that for now. We've talked about that. We'll keep going. Okay, so Lake Hind, here's one of the things they found. And this actually goes back to the Firestone team, because the Firestone team in 2007 got samples from Lake Hind, and they were the first ones to find impact proxies, including nanodiamonds. So here we see the graph that we've looked at showing the peak, the sudden peak of nanodiamonds in core samples from the sediments that were the bottom of Lake Hind. In those core samples at the Younger Dryas boundary is where the proxies were found, including the nanodiamonds, the platinum, and the iridium. So, yes, it says here, Firestone at Alia, 2007, reported anomalously high concentrations of thorium, uranium, hafnium, scandium, et cetera, in Lake Hind and at Blackwater Draw, New Mexico. They also reported a similar pattern of enrichment at two sites in Italy containing layers deposited during the approximately 66 million year ago Cretaceous Tertiary impact, which I find very interesting, that we kind of see that the whole Cenozoic, in a way, is now bookended by impact events. So as it goes on here, unique and distinguishing geomorphic and sedimentological features related to catastrophic floods are present throughout the region to the west of Lake Hind, particularly along the Souris River, and include deep, steep-sided channels that lack tributaries and have a uniform width along their entire length. The 1 to 3 kilometer wide scoured sub-upland zone, we'll look at what that is. But number 3, very important, streamlined hills in the sub-upland valleys and boulder-armored floors on some sub-upland valleys, scattered massive boulder gravel deposits in the valleys. These channels all head in proglacial lake basins, which have been interpreted to have abruptly released their waters and eroded the downstream valley in a few years. The chronology of these flood events is poorly constrained, although researchers have concluded that all flood channels in the Canadian prairies were not eroded at the same time, which of course makes sense because we're ultimately talking about having to get rid of all of the ice of the Laurentide ice sheet. And this didn't all happen at once, okay? So Sun in 1996 presented evidence for a number of floods that impacted on the Lake Hind Basin, and there is evidence for more than one flood in many places to the west. And then this is significant. Most floods appear to have occurred close to or just before 13,000 calibrated years, 13,000 calibrated years ago, including a particularly large one through the Souris River Valley that emanated from glacial Lake Regina. Other channels west of Lake Assiniboine and the Keoapel valleys may have experienced catastrophic floods a few centuries later. Thus, the water-scoured landscape of Saskatchewan downstream from these proglacial lakes as far as the glacial Lake Hind Basin clearly indicates that one or more large floods helped shape this region. So we looked at this. This is what's there now, is the Oak Lake. We saw that unique arcuate feature. And then we saw the sand deposits, which are these sand deposits right here are paleocurrent indicators. And if you look up here at the sand the transport rows, it's called. It's showing the dominant orientation of the flood sediments. And notice how that arrow runs parallel to these sand deposits, which are represented by the gray splotches. So this is showing currents flowing from upper left to lower right. Up here where it says Verdun, down this way to Souris. And in the wake of these sweeping currents moving across the land here, it left these sand deposits in its wake. And so here we have one of the Assiniboine River Valley or channel. You can see it right here. Notice here, Oak Lake. Look at Oak Lake right here. And then just to the north of Oak Lake, we have this wide channel. Here we'll look at a little closer at it. And when we look closer up, we see that we have a very large channel compared to the river that's flowing in it. So this river, the Assiniboine River that's flowing in it, did not create this channel. This is not created over millions of years. For one thing, we know that absolutely for a fact because the glacier, whatever was there before, would have been obliterated by the glacier. So this channel formed, it's part of the process of the glacier disappearing, melting away. And so what we have here is called an underfit river. And anomalously high concentrations of platinum or iridium. Yes, the high temperature magnetic spherules exhibit morphologies and chemical compositions like those found in sediment dated to the Younger Dryas onset at approximately 40 other sites across nearly a quarter of the Earth's surface. So then we talked about the high energy seismic pulse, the thermal pulse, and then we went to a Google Earth image. And right in here, you see there's Oak Lake. Doesn't show up very well on this, but you can kind of see this darker blotch area right here. That is the basin of Lake Hinn. So it was in there, just north of this little town called Hartney, where samples were taken, and the Souris River flows through there. So the Souris River exposed a sedimentary outcrop. A couple of things I want to call your attention to is these dark features here. These are a series of giant spillways. You can see them down here to the left in North Dakota. And then we've got some other interesting things. We've got some uplands right here. Two of them, which are considerably higher than the surrounding plain. And there's a map, roughly the border of Lake Hinn when it was at its maximum extent. So when we go up into these valleys here, these spillways, we begin to see things like this. Now, as you're looking at this, notice here where you've got the squares that are cultivated areas, right? And you can see there's a pretty distinct change, a shift between the cultivated area and the area that can't be cultivated. And again, you look on this side, this here is about roughly 5 miles across. And what we're seeing here is the water limits at the maximum flow through this feature, through this spillway feature. You know, right over here, if you can see where my cursor is, roughly would have been the northern edge of the flow, the paleo flow, if you will.
Let me interrupt you a second, Randall.
Yeah.
The difference in landforms there, you're drawing a distinct difference between the stream area and the areas on either side that look very spongiform. Is there a name for that? I mean, it's like I said, it looks very spongy, very marshy, but it's not.
Hummocky.
Hummocky. Oh.
Hummocks. Yes.
That's great.
Well, now I can actually tell you a little bit about the city, and we'll do that in a solar cycle, in a diurnal cycle. So if you can pinpoint, which you can, I mean, you could literally pinpoint the equinox down to a mere fraction of a second, right? But if you do that, if you can pinpoint the equinox down to less than 1 second,
I've been told that, yes.
look at evidence in kind of two different forms. We have a microscopic and a macroscopic form, are very distinct. And we'll look at some of that. We'll in the next hour, we'll look at some of that. So anyhow, so
This is Cosmographia, the Randall Carlson podcast. This is Cosmographia, the Randall Carlson podcast.
Oceanographer and a paleoclimatologist, missed.
But the experts basically debunked his.
Well, yeah, according to the popular press, the experts, now these other guys, these amateurs like James Kennett and the rest of them, got debunked by the experts.
Yeah.
So James Kennett and Alan West, who I think would be a great guy to get on here and interview.
That would be awesome.
Because he's really almost the spear. You know, he's the guy who kind of helped get this thing off the ground, him and Firestone. This was in the proceeding of the National Academy of Sciences. Biostratigraphic evidence supports Paleo-Indian population disruption at 12.9 Ka. K is 1,000, A is years. So it's just an abbreviated way of expressing 1,000 years. So 12.9 Ka means 12,900 years ago. He's talking about this paper by one of the critics, the skeptics, co-authored by Buchanan. He says that Buchanan et al. Interpret a 40% reduction in the cumulative probabilities of radiocarbon dates at the beginning of the Younger Dryas as noisy data. So, in other words, they're looking at all of a sudden there's at least a 40% reduction in the amount of radiocarbon dates right at the Younger Dryas boundary. So what they're saying here, Kennett and West are pointing out, is that they're basically just dismissing that as noisy data, inconsistent with human population decreases, as would be predicted by the extraterrestrial impact hypothesis. The reduction is, in fact, consistent with other biostratigraphical evidence suggesting an abrupt environmental perturbation at the onset of the Younger Dryas, afflicting human populations. Haynes, who we've been introduced to, C. Vance Haynes, described a black sedimentary layer at 70 localities across North America dating to approximately 12.9 Ka as a stratigraphic marker horizon, where Clovis artifacts and select Rancho La Brean fauna occur just below, but never within or above. So here's a little something more specific on the Rancho La Brean about that. Here we go. It's a North American land mammal age on the geologic time scale. According to the North American Land Mammal Ages Chronology, or NALMA, set from less than 240,000 years ago, a period of 0.229 million years. Named after the famed Rancho La Brea fossil site, more commonly known as the La Brea Tar Pits in Los Angeles. So the Rancho La Brean is characterized by the presence of the genus bison in a Pleistocene context, often in association with other extinct Pleistocene forms such as Mammothus. So Rancho La Brean, now here they're saying, goes back 240,000 years.
Okay.
I don't think it's that critical to know that. Just to understand that when you hear that term, we're basically talking about the megafaunal species that existed at the end of the last ice age.
Right. Can we back up a second? You were saying the point you were making before. They were saying something about there's fewer radiocarbon dates, so it was noisy data. Can you kind of explain?
Well, radiocarbon dates suggesting presence of humans.
Okay.
Yes, radiocarbon dates associated with human activity.
All right.
So, for example, if you had a butchering site where animals are being killed, or you had a campsite where nomadic hunters may have seasonally camped, and while they were there, they left their remains behind.
Right.
You might have trash pits that had bones in them associated, with tools and artifacts. So when you radiocarbon date, there was this sudden drop of 40%, minimum, at least 40%, which the skeptics were saying that's just noise. And the proponents are saying, well, no, that's a real indication of population disruption or decline in population numbers.
Okay, I see what. So the phrasing drop in numbers is talking about, like, if you were looking at it on a graph, you've got time here and number of objects found that dated to that time, and there's just a lot. That's why you're saying it that way. Okay.
Yeah.
All right, I got it now.
Good. Well, thank you for clarity, because sometimes I may go on here and not. It's good that you stop me and we try to clarify these things.
Okay.
I think that's a valuable thing. Because
I didn't know what he was talking about.
Basically, what they're saying is like you get up to a certain time, and there's just a lack of objects that date of human remain objects that date to this specific period.
A precipitous decline in the dating of stuff that would be associated with human activity.
Yeah. And so the authors of the paper are saying, actually, this is not noise. This points to a massive population drop.
Right.
Yes.
Okay.
Got
Makes
it.
Sense.
Thanks. Yeah.
Oh, anytime, guys. Okay. So they go on to say archaeological sites containing both Clovis and immediately post-Clovis material are rare, and where present are nearly always separated by culturally sterile sediments. So in other words, Clovis activity, abundant Clovis activity, 300, 400, 500 years leading up to the Younger Dryas. Now, black mat layer, horizon, Younger Dryas boundary horizon, and now you have what they're referring to as culturally sterile sediments. Yeah. And then after a hiatus of 500 or 1,000 years, you start seeing cultural evidence showing up again. Of the 11 well-dated Clovis sites, none has post-Clovis materials immediately above, suggesting a potential disruption in settlement or landscape use. Folsom age materials, which was the culture that followed the Clovis, the Folsom were the people that show up after this culturally sterile area that he's talking about there. Folsom age materials occur above the Clovis materials, but a hiatus of approximately 500 years is suggested by an intervening sterile deposit up to 35 centimeters thick. So 35 centimeters is about 14 inches roughly.
Wow.
Okay.
Yeah. So when we're looking arrowhead, we dig for arrowheads or hunt for them. Like Clovis, people call Clovis arrowheads paleo points, right? And then there's Folsom points, which are almost as valuable and awesome as Clovis. They call them transitional paleo. They're much younger. So,
well, that would make sense. Okay.
Yeah.
And the radiocarbon dates associated with those Folsom age materials are 12.4 to 11.8 Ka, or 1,000 years ago. Got that?
Yep.
So if the Younger Dryas is dating to 12.9, here's the first Clovis artifacts dating at 12.4. So that's a hiatus of 500 years. And that...
The first Folsom.
Yes, and that's following under this foot-thick layer where there is nothing.
Nothing.
Sterile, they're calling it.
But there's this hiatus of hundreds of years, and then these people come and camp in the same spots. It's really interesting.
Sure.
After everything's been covered up and you can't even tell it was a camp anymore.
Right.
It's real interesting.
He says this is also the case at the well-dated Clovis deposits at Shawnee, Minnesink in Pennsylvania, which are separated from an early archaic deposit, which dates to 11.5 Ka, and by 1.7 meters of sterile deposits. Okay, so 1.7, that's going to be, that's getting up there close to 6 feet thick.
6 feet, yeah. I was going to say.
Yeah, actually just over 5.5 feet thick. When biostratigraphic and radiocarbon evidence are taken together, they point to a post-Clovis decline in human populations consistent with the Younger Dryas impact hypothesis. So that was in 2008. But we can jump ahead to the work of David Anderson, which quite interesting. And here is a new black mat layer photo that I was able to find in the recently published literature. This is going to be found it's in a tributary stream of the upper San Pedro Valley, southeastern Arizona. So I am going to do a share screen here so everybody can see this.
Oh, yeah. That's in Arizona?
Yeah.
Wow. Wow, look at that. Holy crap. That's clear, man.
Okay, you guys, can you see the black mat layer there?
There is no mistaking that. That's amazing.
No mistaking it.
No, I would say right. There's no mistaking that. That's about the most impressive one I've seen. And I think that we might have to go there and document that in person. What do you think, Brad?
Definitely. I was trying to remember if that's in Coal Mine Canyon.
Brad, that's not you in that hat?
No. Yeah, Arizona's on the list. Let's go.
San Pedro Valley, southeastern Arizona. I can find the exact position of this by going back. This was actually published in 2011, Evidence for Younger Dryas, Global Climate Oscillation, and Human Response in the American Southwest.
It looks like the layer is actually exposed on the surface over there to the left.
Yeah, it does.
Right.
Yeah. It's been eroded down to be exposed again.
Mm-hmm.
Well, I think Russ had brought up a pretty interesting point that I'm kind of still thinking about, which is like
he does that from time to time.
Yeah, he does. Looking at that layer, his point was that these people that come hundreds of years later, the Folsom people, come to a site that's been covered by this foot of,
or even
well,
6
you've
feet.
got the black mat, and then you have this foot or up to 6 feet of what was the way it was described, culturally
sterile.
Mm-hmm. So there's no sign that anyone ever lived there, but they end up camping at exactly the same place, even after this catastrophic.
It's interesting
thing that changes the landscape. This is really interesting to me. Why did they pick those same spots? I mean, they're literally burning on the same midden pile in many cases.
Yeah.
Well, the first thing I would do is I would look at topography.
Yeah.
Right.
You know, obviously, adjacent to streams would be,
Definitely.
and you know, this one that I just showed you, as it said, there was adjacent to the San Pedro. What was it? The San Pedro River, right?
Right. It's just, and I recognize, I mean, I realize that, like, we often find midden piles. There's very specific things you can look for, like at a peninsula between two connecting streams or creeks or whatever is often where a campsite will be. So yeah, you know, the topography, the geography of the area will kind of tell, but it's just the fact that they end up having their fire on the same.
Yeah.
You know?
Yeah, that's interesting.
That's pretty cool.
Yeah.
Yeah.
That's pretty cool.
Other than the fact that, you know, obviously being adjacent to flowing water is going to be valuable. And, you know, unless the topography has been drastically changed, now the vegetation's undoubtedly changed.
Yeah.
But if the topography hasn't changed that much, you're still going to have, you know, if there was a river flowing through a valley.
Yeah, or a spring coming out of the ground right there or something.
Yeah, or a watering hole, you know, so they're going to be going where the vegetation is, where the animals are.
Right.
It may not be that much of a stretch that at least in some cases they are going to reoccupy the same areas that had been previously occupied.
So so you're basically saying there was no spirits there saying, camp here, buddy.
No, I'm not saying that. There might have been spirits there.
We got some kind of genetic memory too, though, possibly. You know, how do the salmon swim upstream so far and find the exact spawning place? You know, how do birds fly back to the exact same place? You got some magnetic resonance or some genetic thing that says we've been here. No deja vu.
How do ants know how to farm?
Yeah.
That might be getting us a little bit off track.
But it is interesting. I mean, if you think of, you know, you've got 6 feet of material being deposited, or 1.7 meters of material being deposited, so that implies at least some kind of change of the landscape. You know, you got to change some stuff to put 6 feet of stuff down over a spot, and they still pick that same spot.
Well, you know, like a few years ago when Brad and I were hooking up with Graham Hancock to take him on his research tour for Magicians of the Gods, we had a couple of days before he arrived, and we went up and explored up around Mount St. Helens. Right now, you could see that the changes in landscape were dramatic. But let's see, I don't remember the name of the river that flowed down through there. And even though the topography had been changed considerably, it was still there. The river was still in the same valley.
Still
even
roughly
though you
in the
might
same
have had
spot.
20 feet of ash covering the valley floor, it was still connected as part of this overall catchment basin that was feeding into it. So you could see obviously where the post-eruption river had incised new channels and all, but it was still in the same valley. So, for example, in the San Pedro Valley, you know, it may have been that, you know, there was a river flowing there in, you know, during late Wisconsin times, pre-Clovis, still a river flowing there afterwards. That's what I was going to say. It might be interesting to pull up Google Earth here and take a look at the San Pedro Valley, which I have not done yet.
Yeah, I mean, you're right, because even just a 100-year flood can deposit 6 feet of material in some areas, depending on the nature of the river.
That's true.
So,
and we often find that. We find midden piles that are, you know, half a mile from the river. And the idea is and then there's river gravel. Like you get down to the bottom of the midden and it's river gravel.
So they were on river gravel right next to the river.
They
when
were
they
camping on river gravel.
Yeah.
Sure.
Yeah.
Well, yeah. So I wouldn't look for too esoteric of an explanation there. But that's me. Brad,
No,
if you
I
want to
agree
go and see if you can find evidence of some spirits. Or no, that was you, Kyle, that said that.
I agree with you though. I still find it very interesting that, you know, they're just like, hey, let's start a fire right there.
Yeah, in the exact same spot where the other
That's
fire
just cool.
was.
I think that's really
500
cool.
years ago.
It
Yeah.
tells you something about, I guess, you know, the environment that you're living in. If you're like, we have all this technology, so we don't have to go around recognizing geological features all the time in order to survive.
Yeah.
But they did. They read the land. You know, they had to do these things so you can see that in it's there in the evidence that they came back to these very particular spots.
Yes.
So I just think it's very cool. Very interesting.
Well, it is cool. Yeah, and it's helpful because obviously if you've got one culture there, then you have this sterile layer 5 feet thick or 1 foot thick or whatever it is, and then you have another culture, and the artifacts and tools and things are distinct between the two cultures.
Yes,
I mean,
they're very distinct.
Yeah. To me, that's very interesting stuff. Here I have a Google Earth. Now, I don't know where exactly this outcrop is, but if we look at the San Pedro Valley, I'll do a screen share here, and we'll have a look.
It could be something just as simple as, hey, that's a good fishing hole.
Yep.
Right.
Well, that's what I'm saying. So you can see looks like it's,
There's also stuff about prevailing winds and are there cliffs for shade in the afternoon? And I mean, you know, there's lots of stuff that they look at too.
Yeah. So as I look at this,
nearby,
here's what I would say looking at this. You got the San Pedro Valley, which is pretty obvious, associated with the San Pedro River, right? Now, I would guess that during the Ice Age, this river was here. Although you notice the flat bottom of the valley, a lot of that may be sedimentary accumulation that's associated with the transition, which I would suspect to be the case because we've seen in the Southwest, there's a lot of evidence of very extreme alluvial deposits associated with the end of the last ice age. A lot of the valleys have alluvium on the floor, and that looks to be the case here. So you may have had a 6-foot deposit of alluvium on the floor in this valley.
Right.
And you may have to dig down through that alluvium to find the pre-boundary floor of the pre-existing river valley. But if you've got a river valley here, you know, this is going to be the natural place for people to congregate.
Yep.
Fishing, you know, water, animals are going to go there, you know, and also maybe somewhat sheltered. Let's see the elevation difference here at the, 3248 next to the river.
Not too much water in the old San Pedro these days.
No, I guess not.
I'd also like to point out to all the viewers here, look how smoothly Randall's able to zoom in and out of this Google Earth stuff here. His internet has been upgraded thanks to all you guys that are supporting the show. Yeah.
Yeah, I upgraded. I thought, hey, if we're going to be doing these podcasts, we can't have glitches like that.
Right.
So this is going to be a continuous process of improvement here. So, you know, there'll be little things that come up, no doubt. And if people want to give us constructive criticism, we're cool with that. But check this out here. When you look back here, you can see that there's been a lot of, you can see how this is all part of the watershed here. You see how the water flowing off the mountains into the valley. So during periods of heavy rainfall, you're going to have a very large scale influx of water into this valley being collected off these mountains. So you undoubtedly are going to have a lot of sedimentary accumulation on the pre-existing valley floor.
Yeah.
Well, we'll finish with this paper right here. I think that would be a good idea to finish with this. This is Jesse A.M. Ballinger we're looking at here, it's evidence for Younger Dryas global climate oscillation and human response in the Southwest. Okay, so he goes on to say in his paper that, and this paper appeared in the journal Quaternary International, one of my favorite journals that I try to read regularly, volume 242, October 15th, 2011. The post-Clovis archaeological record of the Southwest has been explained by the early development of a desert archaic adaptation. But those sites have not been identified and dated. The most significant post-YDC Younger Dryas change in material culture is the appearance of groundstone and pinto-type and notched
Thank you, whoever's been watching. I really appreciate it.
That occur between 9 and 8,000.
I think I'm going to sign out 3 hours stream. Thank you, whoever's been here.
Ago. So, what they're just talking about there is these are the archaeological terms for these particular types of artifacts.
Catch you later. Thank you so much.
That are dating between 9 and 8.